This conference will now be recorded.
So welcome back to the second session of day 4. So it's my pleasure to introduce to you our resource person for this session, Dr. Rajat Jain of IIP Vizag, who is going to talk to us on well stimulation technique. Dr. Rajat is currently affiliated to the Indian Institute of Petroleum and Energy, IIPE, an institute being developed as the Institute of National Importance by the Government of India. Dr. Rajat is working as a faculty member of Petroleum Engineering. He received his BTech degree in Petroleum Engineering and obtained his PhD degree from ISM Dhanbad. He has published his research finding in international reputed journals. He was convener of Petroleum and Renewable Energy Conclave organized with the support of Oil India Limited, Uttarakhand Renewable Energy Development Agency, and Uttarakhand Jal Vidyut Nigam Limited. Last year, he was invited to deliver a talk at Petrotech 2019. Please join me in welcoming Dr. Rajat Jain. So over to you, Dr. Rajat.
Okay, thank you very much. It's my pleasure to just discuss on this stimulation. Am I audible? One of you can just confirm.
Yeah, it's audible.
Yeah, okay, perfect. Now, I just shared my screen, so my screen is visible, whether you guys can see the screen.
Your screen is also visible and sound also.
Okay, thank you. Now, so I will start with the presentation. So in this presentation, mainly I will be just discussing on the basics of the stimulation techniques only. And later I will be giving this one or two case studies and some latest research which is going on this stimulation techniques, mainly in acidization and this hydraulic fracturing. So based on the literature available, I just try to put a few findings, which because I can, I guess there are some scholars also there, so it will be good if these things can also be discussed there. And without wasting time, so I will move to slide 1. So yeah, see, why do we need well stimulation jobs or these stimulation jobs? So first we have to understand the basic cause for this, because this is additional investment for any company to go for all these things. Generally, we want a well to be drilled, cased, perforated in case of cased hole completion, and then the production should be coming up once we install the production facilities and once the well is being completed. But these are unwanted things which are being done in the formation. So we start with the formation damage. So how it takes place. So we can have a look on this particular curve on to my right. So here, in this we can see that the radius of damage zone beyond well bore and the production rate. So you can see in the first few feet only, that area we called near well bore region. So in this particular region, you see there's a tremendous drop of production rate. So because of this damage zone, then you can see the damage permeability, though the formation permeability may be very high, but it's in this case it is around RC. But when it is near wellbore region, there is a damage. Okay, and this damage is now reducing this permeability. What is permeability? Permeability is nothing. This is the ease to flow, the connectivity between the pores. So if you have n number of pores in the formation, if these pores they are connected, then the particular fluid will flow easily through across these pores. If these pores are blocked because of the solid invasion, because of the other particles invasion, then what happens? The connectivity between these pores will be less. So in that case, your permeability will be less, and that's how the production will be decreased. Now, in this case, you see that damage permeability is decreasing. So no matter you have very good permeability deep inside the formation, but ultimately the fluid has to come up to the well. So if this area is not very much clean, then definitely you will have a significant reduction in the production. So that's how the formation damage is nothing. It will restrict and prevent the effective depletion. It will also block the flow to the hydrocarbons and all these things. And obviously, because of that, high reserves may be still remaining inside the formation, inside the reservoir, though you may have you might be having very good pressure energy or the pressure inside the reservoir. So because of this, a very high percentage of zone is not contributing to the total flow, and that's why we are losing the flow inside the formation. Now, there are various mechanisms which can lead to formation damage. So clay swelling, the main one, you can say it is better understood, because once you have your well being drilled, then again you have your drilling fluid inside the borehole. Okay. So in this case, what happened? You are developing this differential pressure, because in the overbalance condition, when you have a drilling fluid, mainly this water-based drilling fluid, So in this case, what happened because of this this filtrate invasion, or because of the formation of filtrate cake or the invasion of mud particles, this near wellbore region is being damaged. And if you have the swelling clays like montonite or the smectite group, then obviously they will swell, and that's how the effective permeability or the permeability will be reduced. Then during production itself, you can have this damage. If you have a very waxy and saltine and this particular crude oil having this compositions, and during flow in the due course of time, there may be a deposition inside the pores, and that's how it may again contribute to formation damage. Fine migrations. So whenever there is some clay swelling, or when it during production itself, the particles they are moving. So these fines they may move and get accumulated into particular pores, and that's how they may again damage the well. Then plugging. So plugging again, if you are using maybe in a workover fluid or the completion fluid or in the drilling fluid itself, whenever you are using, there may be plugging of the pores because of the particulate invasion. Then scales and inorganic precipitates. The scales. These scales just because of the mixing of two incompatible fluids. So one fluid, say formation brine having different composition of the ions, and the one which you are injecting from the surface, or maybe for water maintenance job or pressure maintenance job or water flooding. So when you have a different composition of the two fluids, and they have the different ions, then they may form a scale. So that scale again may lead to reduction in the permeability, and that's how it will contribute to formation damage. Then emulsions, because you are using various additives in the drilling fluid, and that's how if surfactants you are using there, you are using various additives which are constituting your this particular drilling fluid. So again, because of the filtrate invasion and all these things, again you may have a formation of emulsion or emulsion blocks near the wellbore region or inside the formation. Again, the change in wettability, since there is a filtrate invasion, then again during even your well stimulation job itself, you are using acid and you're pumping very additives along with this particular acid and some solvent. Then again, there may be some wettability alteration also. So a particular wettability change may again lead to formation damage. So, and that's why there is a invasion of other fluids. Then there is a concept of latent permeability. So all these things will in detail will contribute to the formation damage. So that's how it is better understood in reservoir engineering, how this wettability and all these things are contributing to all these factors. Now moving ahead, so formation damage, obviously it may affect near wellbore region, because if you have a drilling fluid, if you have this thing, so this will not go around 200 to 3000 or 2000 feet inside the formation, but it will mainly affect near wellbore region. But depending upon the formation characteristic, permeability and other things, so it may extend deep into the formation. So the damage can be caused by solids that migrate and block the pores. So here in this image, we can see here is a formation of filter cake near the wellbore region. And why this cake is forming? Because this particular drilling fluid is having some hydrostatic head, and this is the reservoir pressure. So in overbalance condition, this should be like this. So that's why we keep pressure just more than this reservoir pressure, such as to have this primary well control and other things. So in that case, once this particular filtrate will be formed, because it's a permeable media, so there will be filtrate invasion. Before this filtrate is being formed, there is a spurt loss also, which will contribute to the flow of some particles, solids, and the polymers inside the formation. That's how these things will again go inside the particular rock matrix or particular zone, and that's how they will block the particular connectivity. They will be inside the pore space which is available between the grains. And again, and also if some clay is also present, which has swelling tendency, which has got high cation exchange capacity and all these things, then again it will interact with this particular clay and will try to swell. So that's how this swelling will also take place. So then how to prevent it? You can use simply inhibitive mud, or you can use a particular additive which can give you the external filter cake, or which can give you very less filtrate invasion or less fluid loss. In that case, these pores and all these things will not be blocked. You will have better connectivity, and that's how this particular zone will not be having that much significant damage. Now, damage due to drilling that we have discussed. So the blockage of pores, fractures, filtrate invasion, and clay swelling by filtrate. So you can see it has a filter cake. and the cross section of elbow. So once it goes inside the particular, say some highly fractured zone or the zone which is having hypermobility, so this can go deep inside the formation, and that's how it will contribute to the plugging of pores. Once the pores are plugged, we are losing the connectivity between the pores, and that's how the permeability will again go down. Now again you can see why are we worried about this damage near the valve. You see the simple pressure profile is there. See, this static reservoir pressure is not depleting tremendously like this in the beginning. So once it is coming near valve region, because of the skin present or because of the additional, you say, restriction near the valve region, there is a tremendous drop in pressure because of this skin. So what is skin? So in our pattern engineering, we define this skin as a numerical value, which can give you some idea about the damage inside the formation. So S greater than 0, you have damage. S less than 0, value is improved. S equal to 0, no damage. So this is how we quantify our skin in the reservoir engineering or in the petroleum engineering. So then just to, if you have the idea about the skin factor, you have the Hawkins formula and all these things, you can get the skin from the pressure tangent analysis also. So once you have the idea about the skin factor, you can just tell something about the damage extent, how much damage is there, or you can just say the well is severely damaged or it is not that much damage. In that way, relatively you can have some idea. Now you can go and plan for some well stimulation jobs. Now, there may be damage during casing and cementing also. So there may be some filtrate loss from the cement also. There may be plugging by cement and mud solids also while circulating the particular flow. There may be damage during completion also. Once we are perforating, then this perforation job, what we are doing, we are simply say perforating this particular casing and then the cement sheet. So once the perforations are being made, there is a huge amount of debris which is being created, and again if it is the well is not flowed back very efficiently, or then it may again this debris or the fines which are being generated, they may again block the perforations. Perforation nothing, these are in the metal. See, once we complete a well, we put a casing. Once we put a casing, this is a metal casing. So suppose 95/80 production casing we are putting, and we have to cement it. Then once you are done with this drilling, you have to simply produce it. Then for production, you have to put holes. So you have to establish pay zone connection with the well bore. So establishing this pay zone connection with the well bore, you have a perforating gun which will be having detonating cord, which will be having charge debris, shape charge, and all these things. That's how once you will detonate, it will go and penetrate inside the formation. Then that's how these holes will be created, and finally you will get the connectivity established. So now during production initiation also, you are circulating the fluid, and again the from this fluid there may be invasion of solids, polymers, and into the pores and fracture, and that may again contribute to formation damage. Now there is a damage during well stimulation job itself also. Though the well stimulation job, they are targeted towards to remove the particular damage or to increase the pore connectivity or to increase the permeability depending upon the formation type and the job desired for a particular well. So during that job itself also, there is a high chance you may damage the well. So suppose you are having this fracturing job, or you are having this acidization job. So since in acidization, a huge amount of rock and acid reaction is taking place. So in that case, you may have a very good amount of what you say fines and all these things inside the formations. Once they will once you try to flow back, then additional zone which you have cleared or the fracture which you have created, they may again plugged by the debris or by the fines or the migration of fines. So again, during well stimulation itself also you may have this formation damage. Then once you are cleaning a well or circulating a fluid, then filtrate invasion may take place. If some reactive clays are there or the clay minerals are there, then they may again get swelled, and because of this swelling also you may have this formation damage. Then you have used propellant to fracture the particular fracture the particular formation, and to keep that particular fracture open, you are using propellants. So again, the improper placement of propellant or the migration of fines, so all these things will again lead to reduction in the permeability or plugging of the fracture. So again, in all these situations, you may get formation damage for improper plant well stimulation jobs, or during well stimulation technique itself also. Now damage during production phase. So now we are done with drilling, completion, all these things. Now we are not doing anything from the surface to just have some damage sort of mechanism, but during production itself there is a high chance you may get damage. So precipitation of scales. So we are doing some maintenance job, or you are injecting something from the surface, and there is a change in the equilibrium, say pressure and temperature, because they are changing. Once we are producing from the reservoir, from the well, then there is a change in pressure profile of that particular reservoir, that particular well. So because of this, a change in the equilibrium conditions, also there may be a precipitation of minerals, which may lead into scale formation. So again, this scale again will plug the particular zone or particular pores, and again leading to damage mechanism. Again, the asphaltene deposition may take place. Again, it may help in the formation of emulsions around the well bore. So again, this will lead to depletion. This will lead to formation damage. Now, the pressure, the wells which are just nearing the pressure depletion, or which are being depleted to a great extent, they are more susceptible to high pressure wells because of the low pressure things. So they may again get plugged with paraffin and asphaltene. Again, when we are during this production, you have screens or gravel packs which are installed. See, gravel packs, why we use these? Few formations are not that much having, you say, cementation strength. So these sand grains, when they are not tightly held up, they are not tightly bound. So again, they are unconsolidated. So once you start taking production, so because of the drag forces and the pressure disturbances, or because of the change in the mineralogy and all these things, so what happens, this loosely bound sand, they will try to get into the wellbore, and they will be coming up to the wellbore, and that's how this sand is not desired at all, because this will erode your equipment. This is not at all desired. So just to prevent this, we use sand control technique. So this gravel is one sort of technique where you use coarser grains, and which will be having sitting near the particular zone, and that's how they will allow the flow of hydrocarbon, but they will not allow the flow of this sand and these smaller grains. So that's how this. Initially, they have a permeability very high permeability, but slowly when this production is taking place, and the movement of some cells with silt, clay, or mud, or scale, other things, they may again get plugged, and that's how again you have to look for some removal technique. Now, these clays, these are the very troublesome. Okay, so these clays, these are very troublesome because the reactive clay, mainly this smectite, the moment they are they are interacting with water, and what is the source of water for us? The drilling fluid that we are using, or during completion the fluid, or during workover the workover fluid. So if you are using this water-based thing, so again the rock fluid interaction may take place, and because of this rock fluid interaction, when this clay, they are coming in contact with water, they may swell, and when the swelling is take place, that will significantly contribute to the formation damage. So all types of clays are not problematic for us. The clays which are having this swelling potential, which are having high cation exchange capacity, with which we can exchange the ions which are present in the water or the fluid, then they will lead to migration and swelling and disintegration of this particular thing. So they say a sand containing 1 to 5% clay is not a problem. Generally, it is known as clean sand. So a dirty sand, or the sand or sandstone, which is having a clay percent around 20%, or in between 5 to 20%, that may have some clay minerals, which may create a problem for us and leading to a formation damage. So as I said, all clays are not a problem for us. So just by simply seeing the clay percentage, that okay, clay is 20 or 25%, it will create a problem once we use water-based drilling fluid, or once we have rock fluid interaction. So this is not the right statement to say, because unless you identify in this 20% what are the clay minerals, the types of clay minerals. So once you identify all these things, then you, okay, if this particular clay mineral is there, or other clay mineral which has some rock fluid interaction high magnitude, then it may create a problem during this drilling, or during this particular well operation. Now, as I said, the foreign waters, or the filtrate loss from the drilling fluid, cement, completion fluid, workovers, stimulation fluid, they may again create a trouble once they will interact with the rock or the grains in the particular formation, mainly the clay minerals or the clay. So smectite and mixed layer clay, they got very high swelling and water retention capability. So once the clay presence you have identified using the XRD techniques or all these this particular thing, then you can say there is a chance that permeability damage may take place. Okay, so again, a degree of damage will depend upon the type and concentration of the clays or the particles present. So yeah, this statement I read somewhere that during production itself, when there is no interaction between the rock or fluid, or there is no particular damage done by you during production itself, when you have very high flow rate alone, with no change in environment condition, this will cause the particle migration. So when this particle migration is taking place, so they may go to a particular high permeability zone, or they start getting accumulated there, and that's how they will lead in the reduction of the pore connectivity. Now, there are other these damaged things have been categorized in mechanical, chemical, and thermal and biological. So depending upon the operation that we are doing, suppose we are injecting fluid from the surface or doing some injection job, so that particular thing may have some bacteria or something like this. This bacteria again may go inside the formation, and that's how they may lead to the absorption or the precipitation or something, some sort of this thing. Then again, that may cause a biological damage. In thermal damage, you will have this, we are doing this steam injection jobs, or we are doing in situ this combustion jobs. So again, at high temperature, there may be a mineral transformation may take place, and there may be a generation of the gases. Okay, hydrogen sulfide and other. So these gases again, all these things again may create trouble for us and will lead to formation damage. In chemical, there will be a interaction between rock and fluid, and because of that clay swelling and all these things, again you will have this formation damage. And in mechanical, the migration of fines and all these things, or simply when you have open hole, you are using drill bit or the tool which is directly creating trouble or interacting with the particular page zone, sensitive page zone, that may again cause a mechanical damage. So this is a deep thing, how this particular damage and other things are there. So just to summarize, we have discussed how these things are contributing to formation damage, because once we understand the type of damage, the extent of damage, then we can very easily figure out what kind of stimulation technique we can use, and so that's how it will lead to a very effective job, because every job require a good amount of investment and the infrastructure. So once we identify the type of damage and the how this damage has been done, and then we can easily pick or choose or select the particular well stimulation technique, then in that way you can simply plan a very efficient well stimulation job. So scales, we have discussed how the scales are contributing to this. So if you have two incompatible fluids, or the fluid having different minerals, then they may crystallize, they may precipitate, and in that way you will have the formation of scales. So if you have a two different fluid, one is having soluble salt of barium and strontium, and another is having sulfate, so when these two will mix, so they will lead to the barium sulfide and strontium sulfide scale in the formation, or inside the tubulars, inside the pipe. Similarly, it goes for calcium ion and sulfate ions. So when two different ions they are mixing, due to mixing of different fluids, then they may lead to crystallization, precipitation of the ions, and that's how they may generate these scales. Okay, now we can identify using XRD. So this technique, you can identify the scale by getting the characteristic peaks. If you have some kind of scale, and this you can utilize different solvents, say water, you can utilize acid salts to dissolve it. So this is just summary. So you have some sodium chloride, you can use water soluble scale. If you have some this calcium carbonate, or this iron carbonate, all these scales you can use acids to dissolve these kind of scales. Some scales are neither water soluble, acid soluble, so you have to use intermediate compounds, or you can use directly commercially available solvents or the additives with the service companies. They will form the intermediate component. That component will again be dissolved with the acids. So scales, so once there is a pressure change, temperature change, or incompatibility between mixing fluids, this scale deposition will take place. These are a few images. You can have a scale inside the pipe, tubular. You can have tubular here, and this one image for barium sulfide scale. So again, once these scales are there inside the formation, or they are blocking the pores, or they are simply reducing the pore connectivity, you have to just dissolve the scale by, depending upon the type of scale, you can use a particular thing. You can use water to dissolve a water soluble scale. You can use acid to dissolve acid soluble scale. Now, how do we identify the or diagnose the damage? So using this well test analysis or pressure tangent analysis, you got this, you got various plots. So utilizing that particular thing, you can get the value of S, and if S is negative, whether S is positive, whether S is 0. So in that way, you can check whether skin factor is suggesting you to go for well stimulation job. Then you can have the logging surveys, production logging survey. You can check the you can identify the particular zones which are contributing to low flow rate or this. In that way also you can go for this diagnosis of damage. Now you can, based on the history of that particular operation, or the operation which has been carried out for this particular well, say well completion reports, or over, or the drilling fluid design, or the composition of a drilling fluid that we have used, the high solid mud system, low solid mud system. So based on all these things also, you can simply say, okay, there may be a chance that the damage may take place once we go with this kind of particular fluid or in this particular formation. Now you have other techniques which are very well utilized by the people, the experts who are expert in this. They can simply go for X-ray diffraction test and all these things for the rocks, because we are generally during coding we get pores, and returning we get this mud cuttings also. So you can have this pores and mud. You can go for XRD, and you can have a plot of intensity versus 2 theta, where you can check the characteristic peak of the clay minerals. So suppose you identify a particular clay mineral which has got high swelling potential and all these things, then you can say, okay, once I use water-based drilling fluid, or when there is a filtrate invasion inside the formation, then if this particular mineral is present, this will react, or this will interact with that particular filtrate, and that's how swelling may take place, or suppose disintegration of cuttings and all these things may take place there. Based on the production history also, you got production data. So whether this particular, there is a significant drop in the production, and whether the production profile is going very low. So based on that also, you can say, okay, some damage has been done after carefully examining all these particular reports. And in that case also, you can say some damage has been done, and accordingly you can plan for well stimulation job. Now coming to the stimulation, so generally we have the production naturally because of the this compressibility of fluids, their mobility and connectivity between the pores. So we call that ease to flow. So this is connectivity between the pores. So the permeability. So if suppose the formation may be low, or the formation may be damaged, so it will not contributing to the desired flow rate or economic flow rate, then you have to choose the well stimulation technique. It is not like that every time there will be some damage only, then you have to go for well stimulation job. No, there are a few formations which have got inherent very low permeability, like shale. So in case of shale gas, they got very low permeability, like in nano darcy, sometimes very low 0.1 milli darcy, like that. So in that case, even though you have not done any damage during surface operations, or due to various operations that we have discussed in the previous slides, but still you will intend to fracture that particular zone, or you will try to establish or increase the permeability or include in the pores, because that particular zone is, or that particular formation or the type of formation will not give you or may not give you the desired economic production rates. So in that case also, we try to stimulate the well, even the non-damaged formations also, which has got very low permeability or low pore connectivity. So so we can say the stimulation job, they are targeted towards to improve the pore connectivity. Okay, so mainly the low K rocks or the low K reservoirs, and they can also help in removing the damage which has been done. And so they can remove the damage, and so simultaneously they can increase the permeability inside the formation for low permeability rocks. Okay, so they can also increase the effective wellbore radius. You can have better connectivity between the wellbore and the formation by simply having more hydraulic fracturing or the hydraulic channel. So that's how to establish better connectivity. Now the stimulation techniques, they are categorized. So we have acidizing. So in this acidizing, depending upon the flow rate and the pressure, you can have this metric acidizing, as well as you can have this fracture acidizing. So it depends what kind of pressure you are using. If suppose you are intending to fracture a particular or break the particular formation, then you have to inject at a flow rate, or you have to inject the pressure more than fracture pressure. So suppose for a particular formation the fracture pressure is say for 4500 psi, then you have to inject the fluid from the surface. You have to in such a way such that this pressure should be more than this. That's how the formation will break down. So once you will break down the formation, then the particular fluid, whether acid or the propant or whatever you are planning to put inside the fracture, in that way that particular job is being done. Normally in metric acidizing, we are not intended to, or we are not targeting to fracture a particular formation. So in that particular thing, we are simply trying to inject below the fracture pressure. So simply placement of acid will be there inside the formation or inside the zone, or that zone which you are looking for. So now, so obviously when we have a different injection pressure or the injection rate, so the objective will be different. So in normally metric acidizing, we are looking for near wellbore damage, or to remove the skin damage, or to change the permeability, or to change the connectivity between the near wellbore. So maybe few feet from the reservoir, or from few feet from the wellbore. Okay. Now here, since the reaction is involved, the rock and the acid, they will react, and so that's how the acids, depending upon their acid strength or their acid reaction rate, so the spending time may be very short. So even in 1 or 2 feet only, the acid may completely be spent, and simply your this near wellbore region which is being affected maybe few feet only. So that is the thing which you are having in the case of acids, because the reaction rates are high. So you can use retarders, you can use additives which can increase this spending time, so that acid can go deep inside the formation. Okay, so that's how this acidizing job is targeted toward the few feet from the wellbore. In fracture acidizing or in the hydraulic fracturing, we are simply fracturing the formation, and that's how we are simply fracturing the formation, and just we are going deep inside the formation. So here the objective is to create a linear flow channels inside the formation. So this fracture acidizing is an alternative to hydraulic fracturing and propping. So in carbonate reservoirs, so that's how this fracture acidizing. So once we will fracture a particular formation, we will have acid there. This acid will go inside the particular created fracture, and when this fracture is created, so since there is a heterogeneity in the reservoir and the carbonate formation, because of that you will have some etching will be there. So etched fractures will be created, and these non-uniform fractures, once you release the overburden pressure, they will not be closed completely. So the fluid can flow easily through these particular created fractures. In hydraulic fracturing, we have to put propant. So that's how once the overburden pressure will be there, these will not be closed completely, and that's how you will have the fracture conductivity established. Okay, so the problems in the fracture fracturing job, so you have a huge amount of unresolved fines. These fines migration may take place, and this will go sit inside the particular created fractures, and again this plugging may take place. So we are using some additives there also, so there may be chances of emulsion formation with the formation fluid and other things. So again there will be some blockage there inside the formation. Now this is one image where they are suggesting there's multiple stages of injection. We will have better you say fracture length, or the reduced acid loss inside the formation. So that's how this is one step, and this is three stage injection. So they have given the images of these 4 samples, and they've suggested that this particular things, their fractures are there is a more you can say dissolution there, so better connectivity is established in these multiple stages. Now various types of stage acid that we can use: HCl, HF, acetic acid. So depending upon their acid strength and this ionization power, so these acids are categorized. And so for HCl, they generally targets the carbonates. They will dissolve carbonates, chalk, dolomite. And HF, they will generally target the clays and the for natural clays, or the clay or the additive which has been injected from the wellbore, maybe in drilling fluid. So it can dissolve that particular thing and will remove the damage. Okay, so acetic acid is easy to inhibit against corrosion. And this sulfomic acid, this is available in powder form, so you can just simply transport and bring it to rig site and simply dissolve in the mix with the water, and then again you can inject it. So that's how, but it is more expensive than HCl, and it got some temperature limitations also. Now, in addition to these acids, you require additives also in this acidization job. So these additives, you can use surfactants. Okay, so just to have some change in interfacial tension and surface tension, you can use you have to use corrosion inhibitor because you are injecting from the surface. So tubulars, all these things, they will have they are in contact with this acid. So you have to inhibit those particular tubulars from being corroded, and you have to use fluid loss control adhesives, some polymers which will be used so that once you use these things, so there will not be significant loss inside the formation. Then you can use diverting agents. Generally, what happens in the acid will follow the least resistance path. So suppose a zone which is having relatively more permeability than the adjacent zone, so whole acid will go in that particular zone. And when the zone is particularly be dissolved, so again the permeability of that zone is getting increased. So the zones which are having least permeability, they will not be getting that good amount of acid. But we are mainly targeting our low permeability zones. But because of this particular thing, we have the acid is not going to the low permeability zone, or it is not being uniformly injected into the long section. So in that case, what we use diverting agent. You can use mechanical diverting agent. You can use ball sealers. You can use chemical diverting agent, which will form the temporary plug. Some flakes you can use. They will plug the high permeability zones, and then obviously your acid will be diverted to low permeability zones. And that's how this with the help of the diverting agents or diverting techniques, you can promote uniform injection into the long sections. Okay, and you can also you have used some iron precipitation agents and suspending agents just to have the job done efficiently. So the various surfactants which are available in the commercial names are giving. So these surfactants are available. So you can have they give the properties like this. So and based on the particular job, you can choose the particular surfactant. So non-anionic, anionic, and you can have the combination of non-anionic and anionic also. So whether they are water weight and oil weight, okay, they are what their solubility, whether they are dispersible in oil or their salt tolerance, salinity tolerance. So all these things they give, and then accordingly one can choose, and then the job can be done. Now, once the surfactant, they say the sulfonates, phosphates, and phosphonates, sulfonates. So having this particular these things, it can be categorized in anionics. Okay, so anionic surfactants is water soluble group. Amphoteric, this is water soluble group, so both negative and positive. So these cationics are mostly amine compounds. Okay, these most ionic compounds are organic molecules. So current toward non-anionic. So normally cationic and anionic we don't use together normally, because that may yield to some insoluble precipitate. So again, this will be a problem. So accordingly, depending upon what kind of surfactant you require, and depending upon the properties, you can choose the particular surfactant. Now, carbonate acidizing. So once we are talking about acidizing, so we got a different formation. So say in carbonates we got a dolomites, limestone, and one formation is sandstone. So in carbonate acidizing, the objective is to clear near wellbore damage and also create linear flow channels by fracturing and etching. So here we remove the near wellbore damage also, or we intentionally create some linear flow channels. We establish the connectivity between the whether the natural fracture which are present there, or we establish the connectivity between the pores by fracturing. You can have the fracturing, or you can have the acid fracturing also. Now, the major problem with the acid is they tend to react very fast with carbonate. They will spend near the wellbore. That's why you will not get that deeper penetration inside the formation. So the problem with the homogeneous carbonate is that they will generate smooth fractures. So you see, we have overburden pressure. So suppose we are fracturing at say 6,000 feet. Okay, so this overburdening strata, this will have some overburden pressure on the created fracture. So once you remove the treatment pressure, once you remove this particular injection pressure, the created fracture again may get closed because of this particular overburden pressure. So what happened in acid fracturing? This particular fracture is non-uniform in size, so it got some edges. Because of that, so once you remove this particular thing, this will not be completely closed, and you got still some channel to flow. But in case of relatively homogeneous formation, because the formation is homogeneous, you will not have that much etching thing as compared to heterogeneous formation. So again, you will have a smooth fracture faces. So once you remove the injection pressure or the treatment pressure from the surface, or you will shut the pumps, then definitely because of this overburden, it may get closed, and you may have low fracture conductivity. So heterogeneous formation, we can target this carbonate acidizing. So in that case, you can go for hydraulic fracturing in the homogeneous carbonates, where you can have the normal propant, which will establish the connectivity. Now, for deeper penetration in fracture acidizing, because the acid will tend to react with the formation immediately, so you will not get that much deep penetration. But in fracture acidizing, we are targeting the formation as deep as possible, just to create linear flow channel. So in that case, you can use retard the acid by putting some polymers or putting some additives, so that the acid retarded acids can give you some deeper penetration. So if your wellbore is plugged 90% near the wellbore, if you have this 90% plugging, so if you restore the permeability, if say few 5 feet or some 6 feet, then you can have increase in production around 350% or more. That is the significant of the removal of formation damage. So that's how if you do the job, if we can do the job effectively, then there is a significant increase in the production, provided the formation is having better permeability and the damage is because of the near wellbore damage. Then in that case, by simply removing the formation damage near the wellbore, we may have good amount of increment or good amount of production hike once you remove the damage. Now, in the case of homogeneous formations, as we have discussed, it is very difficult to get the particular non-uniform fracture. So you can have a viscous preflux before the main stage. You can have some viscous gel or viscous polymer gel inside the formation, homogeneous formation. So once the acid will arrive, so because of this viscous gel being present there, acid will be diverted into different portions. So in that case also, you can have etching by acid channeling. So in that case also, so irregular etching you may get, and you may have this non-uniform fracture. Okay, so acid fracturing we do about fracture pressure, and here we have the conductive wormholes. See what happened because of this carbonate having different properties and the pore size or the works and the fractures. So there will not be pore of uniform size. We may have a pore, big pore, small pore, and all these things. So the pore which is having a bigger size, the acid will try to go there, and this particular pore will further grow more, and will receive more acids. So that's how these wormholes are being created in the carbonate acidization, or normally acid fracturing in the carbonates. Okay, and by simply etching these particular wormholes or the fractures or vacation of wormholes, we can have the increase in the conductivity. Now, this retardation of HCl, so regular acids, this is a test time versus the HCl concentration, how this acid is being spent. So this within 20 minutes, this acid has been spent up to less than 3%. But once we use the chemical retarders, we use the polymers or gels, this particular spending thing we can decrease, so that the formation can go deeper inside the acid can go deeper inside the formation. So if we can see the polymer gel acid, the chemical retarded acid. So that's how this retardation of HCl can be achieved by using of some chemicals. And once you retard this acid, once you slow the reaction rate, then the acid will not be spent completely near the wellbore region. It can go slightly deep inside the formation and can do the job effectively. So these are the wormholes which are being created by acid dissolution of limestone. So this is one the core flow study, or the there. So typical wormhole pattern found in metric acid treatments in carbonates. So acid was injected into a cylindrical core prepared from the carbonate rock or representative rock. So when the reaction rate is very high, very fast, you can have simply one wormhole that's extending, and when you have say you have which can retard the acid reaction rate, or which can slow the acid reaction rate by involving some surface acting retarding agent. So you can have multiple wormhole there inside the formation. So that's how, depending on the flow rates, the generation of wormhole again change. And even though we are using same type of acid, same concentration, same additives, but because of the acid reaction rate, because of the change in mineralogical composition, the job may give you different results. So these pores are of different sizes in carbonate. So because of the Vogg's hairline fracture, so the heterogeneities will result in the channeling and wormholing. So again, this Fogler he gave the simulation results. Once you have the flow rate of Q, you will have this type of distribution. Once you increase the flow rate by 10 times, tenfold, so you will have distribution like this. So this is a particular numerical simulation result for the acid radial flow. Now, typically, once we fracture a carbonate rock, so simply once you pump the acid inside the fracture, so that acid will etch the fracture faces, and then what happens? You will have the conductive wormholes, or you will have the rough fractures, non-uniform fracture faces, and that's how you will have this fracturing done inside the carbonate. Now, the acidizing in sandstone. So the target is to increase permeability by dissolving clays near the wellbore. So these clays can be your natural clays which are there inside the formation. Or these can be the clays which are being injected from the drilling fluid, or the solids which are being migrated from drilling fluid inside the formation. So if you have a sandstone with 20% or more carbonate, you can use SCl only. And HF acid, it can target carbonate, calcium carbonate, sand, shale, feldspar, and clay. But with calcium carbonate, hydrofluoric acid will generate insoluble precipitate. And this insoluble precipitate will again a problem for us, that is known as calcium fluoride. So once you have a calcium carbonate, it is better to use some pre-flush so that this calcium carbonate can be dissolved. And that's how once you are using 3% HF in the main stage, this will not be leading to a precipitation of fluoride ions or calcium fluoride. Generally, typical mud acid, we use 3% HF and 12% SCl in the main stage. Before that, we have pre-flush stage, and after that, we have post-flush stage. So then that's what we have discussed. So HF acid, it may react with limestone, that is calcium carbonate, and it may lead to calcium fluoride, which is an insoluble precipitate. So avoid this. You can use pre-flush of SCl, because this will dissolve the carbonate and will give you CaCl2. So that's how it can be done. Or you can simply use NH4Cl, the pre-flush, or after. So in the absence of carbonates, so we don't require SCl and all this. You can use normally, you can use diesel oil, kerosene, crude oil, ammonium chloride as pre-flush. So normal pre-flush, you can give 5 to 15%. Add additives, surfactant, corrosion inhibitors, mutual solvent. Mutual solvent will use because this will prevent the absorption of these corrosion inhibitors or surfactant on the rock surface or the sand face, the sand grains. So that's why we can use mutual solvent. And in HFSCl acid treatment job, you can have 3% HF, 12% SCl. After plus, you can give just to displace the spent acid, or just to get the job done efficiently. You can use after plus. So if some unspent or spent acid is there, some additives are there, so you can push them inside the deep inside the formation, or you can also prevent the precipitation of ions or the formation of emulsion. All these things you can do with the after flush. So in that way, you can go for after flush, and that's how you can have your main job done. So normal field procedure, this way we have to first choose the well which is having positive skin factor. So you can utilize pressure tangent analysis, well test analysis, build up and draw down, all these techniques you can utilize, and then you can have your skin factor calculation. If the skin is positive or the well is damaged, you can go, you choose that particular well, use 5 to 15% chloride T-flush. So this pre-flush is required so that we can avoid the precipitation of some ions, iron ions. So in that case, it can also make the environment suitable for the main stage job. So this pre-flush is required, and then you can have, come to main stage. You can have some standard procedure, 200 gallons of 3% HF, 12% HCl. But obviously it will depend upon the rock composition. This is not a thumb rule that we have to use only 200 gallons for this particular concentration of acid. But normally standard acidizing procedure given by Robert is like this. Now you can use combination of anionic and non-anionic surfactant. You can use non-anionics alone also inside the formation. So this surfactant, once the job is done, it will help us in getting the acid back, spent acid back up to the surface. You can, if some perforations are plugged or you require the perforation to clean, then you can use clean water or oil to break down the particular perforation in case they are plugged. Then why are we using mixed solvents? You can use modified glycol ethers, so they will prevent the absorption of surfactants, corrosion inhibitors on the rock surface. So they will not, it will not further lead to formation damage. Then when the acid job has been done, the spent HF acid near the wellbore can be flowed back, and you can have the flow established there whenever it is possible. So these are the things, trailer mounted SF pump which can use in the well stimulation jobs. You can have a pumps also, which have the blenders and these things. So that's how these are mobile. You can use it and bring it to the rig site, and then you can have your job done. Now we can summarize what our treatment job is intended. So it can dissolve clays, mud solids near the wellbore. It can, so after the job is done, there should not be precipitation of any insoluble say compound, which will further lead to the damage, because our intention is to clear the damage. But because of the presence of various ions or all the change in the concentration of the system, it should not be precipitating. So that's how the precipitation of insoluble substance should be prevented, or you can use some additive just to minimize this particular fundamental. And you can prevent this spent acid from emulsifying. It should not be mixing with the formation fluid and making an emulsion there. So we can use surfactant or additive which can prevent this particular thing to be taking place. And now we will leave the sand or the remaining fines after the job in water wet condition. So it is mentioned that these water wet fines or they are much smaller in size as compared to oil wet fines. So they can more readily be flowed back, or they have more mobility, so they can be flowed back to the formation the wellbore easily after acidizing. So later, once we have production of the movement of hydrocarbons, this will not cater trouble by blocking the pores and other things. So that's how I think they have said it has to be in water wet condition. So spent acid should have low surface tension, low interfacial tension, so such that when we are trying to flow it back, when the job is done, it should return very quickly to the wellbore. This is the summary of what we have, how the mechanism there and the remedial measures, whether we have to go for acidization, fracturing, or some solvent or surfactant treatment. Depending upon the operation, we have drilling, cementing, sand control, completion, workover, production. So every operation which we are doing from the surface, it may lead to some damage depending upon the composition of the fluid that we are injecting, or depending upon the formation characteristic, formation composition. So according to that, we can choose the particular remedial technique just to remove that particular damage. Now, since the acid is involved, so we must take care of safety also, because the concentration of acids or inhalation may cause these respiratory problems in the human. So that's how the vapors of the acidic and anhydride. So that's why these are very irritating. These are very problematic. So the acid is by accidentally, if it's touching the surface or the skin, it may cause severe burns. So special care should be taken while transporting these acid or chemicals, and they should not be contaminating your clothes and these things, otherwise it will be a problem. Somehow accidentally it has been contacted, you use soap and water immediately, so that the extent of damage or extent of burn should be minimized. Now hydraulic fracturing, how it works. So it is hydraulic fracturing, it is intended to create the increase the permeability of a particular formation. So here a huge amount of water, a gallon of water is required, million barrels of water is required, and some additives we use for polymers just to have the viscosity. Okay, so we can use guargum there. So that's how these particular viscous fluid we will pump inside the formation. So there are two stages. Once we have pad stage, when we have slurry stage, in pad stage we simply inject the water with some chemicals, additives, polymers, which will go inside the formation, will fracture the particular rock or break that particular rock. And in slurry stage we inject the sand and the propane. You can have propane which will go inside the formation, and once you remove the treatment pressure, once the pumps are in certain condition, that fracture will not get closed completely because of the presence of propane. So the selection of propane and the placement of propane, all these things will create a crucial role, because they will affect the fracture conductivity. So typical this fracturing profile will be like, you will have a first breakdown pressure where the fracture the fracture will start, initiation will take place, and the formation is just breaking. And after this, once you have another stage as a fracture propagation, once the fracture has been broken, the propagation of fracture will take place, and finally you will have an instantaneous shut-in pressure, means the pressure which is required to keep the fracture open. So typically you will have this particular profile once you are going for this this hydraulic fracturing job. Now, the critical part is how to choose a particular fluid. So since we are injecting propellant inside the formation, that may be a sand or bauxite or other ceramics, so it should be having very good transporting property. Viscosity should be good enough. It should be having good suspension capability, because the fluid will be going deep inside the formation, and it will be subjected to various shear rates inside the formation. So based on that, you can select a particular fluid. You can do some rheological studies at lab. You can do some scholastic studies at lab and check what is the gelling property and all these things, so that the propellant transportation and the suspension should be efficiently done. Commonly used sand and bauxite. Sand, this can be used for all type of reservoirs, relatively less expensive than the bauxite. Should not contain more than 5 to 8% fine. So that's how we can use sand. Sintered bauxite. Bauxite is having highest strength propellant. So so design fluid should be having more viscosity, because about this having more density as compared to sand. So here you can see how these propellant are being placed. So you can see partial monolayer, monolayer, and you can see the arrangement of typical propellant and how these propellants are keeping the fracture open. So once you remove the treatment pressure, because of this overburden pressure, these propellant, they will be helping you in maintaining this fracture open. So obviously their compressive strength will play a significant role, because once the treatment pressure is released, the propellant they should not get crushed. Otherwise, otherwise it will be a problem in terms of low fracture conductivity, and the job will not be that much efficient. These are the images of various propellants and the types formation. Now, one or two case studies we can see how what is the research which is going on, or the research which has been done so far. So here in this thing, they have used one organophosphonic acid complex having 5 hydrogen ions, so something related to chemistry. So they have utilized this particular chemistry fundamental, and they have developed these acid systems. So RH system, regular hydrogen chloride, hydrogen fluoride acid system, and this IHF is your improved hydrogen chloride, hydrogen fluoride acid system. So that's how they have developed different mud systems: acid A, acid B, acid C, acid D, and depending upon, they varied the composition of acid HF, HCl, acetic acid. So once they have this HV is your organophosphonic acid complex only. So they have varied this one, and after that the representative core samples has been collected, and when these they did the mineral characterization, they have identified the mineral, they did the quantitative analysis also. So you can see at the bottom total, the clays 50% in core sample 1, 59%. So the clay is present in good amount, and that this smectite is there. So again, as we have discussed previously, smectite will have some swelling potential. It may lead to significant formation damage. So based on this mineral characterization, they further went for this core flow test. 1000 psi overburden pressure was given, and this overburden pressure is just the confinement pressure, just to simulate the actual wellbore conditions. So this acid system, they have used, they measured the initial permeability with the oil, then they damaged the formation with xanthan gum or drilling fluid. So once the formation is the core has been damaged, there is a reduction in the permeability, and after this they went for acid injection, and this the different acid system, they try to remove that particular damage which has been done by mud in the lab, and overall results they have reported. So we can see this IHF FAS is giving some encouraging results. So this 70% they have claimed that it's improved the permeability up to 70%. So that's how based on this particular laboratory result, they went for field trial. Now in field trial, this typical say injection rates, how they have used, and they have pumped this particular say mud system, improved one, inside the offshore well, which is having a water depth of 4,326 feet, and the casing was set at 10,748 feet. So once it has been injected, then based on this production data, they have said that the skin factor was significantly improved, and the production was also increased. There was a production of water around 30–40% along with the oil. So utilizing this particular thing. So self-propelling fracturing technology, generally what we have discussed in conventional fracturing, we are simply using this propellant and this sand or the bauxite and other ceramic to keep the fracture open, such that this fracture will not close because of the overburden pressure or the stresses inside the formation. Now there has been a recent development or the thing in the self-propelling fracturing technology. In this, we are not using any propellant or something. What will happen in this, we are having two fluid system. One is CFL, that is channelized fracturing fluid, which will create fracture inside the formation, and another is self-proping fracturing fluid, that is SPFL. So when these two will go inside the formation, and there is a phase change because this SPFL is sensitive to temperature. So when there is a change in the temperature, this solid free liquid, or this will turn into some self-proping solids or SPS. So when when it will go inside the formation, and in the formation there is a temperature change, there is a elevated temperature, so it will go to a phase change as a thing, and it will turn into a solid particle or a particle. So this particle will keep your fracture open. So from surface, here we are simply injecting fluids only. We are not injecting, in this particular technology, we are not injecting any propellant or something. So which will and because of the chemical property and because of the chemistry involved in this particular operation, there will be a change in phase, and the particles, the solid particles, or the SPS, they will form in situ inside the formation. Okay, so they have mentioned it is around 5 hours they took for this particular thing to take place, but with the help of some additive or phase change temperature additives, this can be reduced to 30 minutes also, depending upon the job which is required at the particular well. So once it is done, you can flow back your channelized fracturing fluid, and this SPFL, which has been not turned into SPS, will be retaining there, will be sitting there, and will be giving you a more conductive channel. So this is what they mentioned. They have used all these chemicals there, and so they have developed one system, A305. Then you have used all these things related to chemistry, and then they have used the vinyl acetate and other additives also just to develop this SPFL. So this is the image, liquid to solid phase transition at different test temperature. So they have shown the effect of temperature, how this phase transition is taking place. So you see 30 degrees Celsius, 60 degree, 90 degree, and finally 120 degree. So they have got this phase change temperature dependency on this temperatures, and which is there because from surface what we are injecting at surface temperature. But when it is going deep inside the formation, the temperature will be changing. So because that particular thing can be is being utilized here, and because of the change in temperature and this phase change is taking place, and this development of SPS is taking place. So you can see in image one they are injecting CFL and SPFL, and then this may be the morphological or the distribution of this SPFL inside the particular zone, and then because of the change in temperature, because of the thermal sensitivity of this SPFL at formation, this particular solid particles are being developed. Again in image D, it is the further distribution of this SPS. Then again what we are doing, this CFL is now being flowed back up to the surface, and because the fractures are still being opened because of the presence of SPS, and then this conductivity is retained. That's how this oil and gas will flow through this SPS. So that's how this all being summarized here. So CFL and SPFL, they claim it is immiscible. Okay, and the CFL controls the distribution of SPFL in the fractures. Okay, and to develop self-proping fractures. Thermal sensitivity of this particular SPFL is just triggering this formation of SPS. So this will again, the particle size is around 40 to 70 mesh, and in this particular job. And again, they have used two systems, slick water, and you use guargum based system. So this particle size little bit varied in there, but it is I think it is below 100 only. So this distribution of particle size was there, and again we can they claim that it can be again improved. SPFL improvement, the distribution can be again be controlled by simply varying some parameters like interfacial tension, density, displacement, and proportion, the amount of the concentration that we are using. So based on that also, this distribution of SPS can again be still controlled. So that's how that has been mentioned in that particular research. Now again at one more image where, so this is for guar gel based CFL, and you can see before stirring 60 degree, after stirring 60 degree, and 100 degrees Celsius, there is a phase change, and again finally for filtration and separation there will be some solid particles like this. Again, for slick water, you will have the change in temperature. Because of that change in temperature, again it is yielding into solid, the image D, the bottom. So you can have this SPS generation here. So this was the image of the field aerial view of that particular system. So you don't require too much special equipment for this job, because you don't require to mix that particular sand and all this thing into the slurry state. Simply with the help of fracturing bender track and or normal fracturing equipment, conventional thing, you can utilize this particular technique. So the rock was fractured using viscous fracturing fluid, and this is the injection rate that they have used, or the flow rate. So finally concluded that this phase temperature can be adjustable. Adjustable. You can use by using some additive, and they have said that it is having a good compressive strength and a high compressive strength. So even at high overburden pressure, it will not get crushed, and your conductivity of the fracture will be retained. So further research and further investigation is required to explore the complete effect of this SPFL and this self-propelling fracturing technology, and people can try and just look and explore further how it can be done more efficiently, and what are the other factors which are controlling this particular thing. So at IIP we have these things which can be contributing to this particular research. So we have four plugs, we have four holders, we have liquid parameter, gas parameter, which can be simulating the actual wellbore condition. We can go up to 6,000, 7,000 overburden pressure. We have syringe pump, which can give you a constant pressure injection, fluid injection mode up to psi. We have surface tension or contact angle measurement device, which can measure the surface tension of the fluid, maybe acid, maybe fraction fluid, which we are using. And we have this acid resistance core holder for this core accumulator also, or the fluid accumulator also, which can help in pumping acids. So the material is acid resistance. And finally, we have this rheological measurement rheometer, which can give you the rheology of a particular fluid which has been developed in the lab, and simultaneously we can decide whether this particular field will retain these properties inside the formation at various shear rate conditions. So these are the references where these things have been taken. So finally, we have this question and answer session. So we can take few questions. We'll try to answer, and later if you can also get in touch with the email, send email, so I can get more answer for the query. Okay, thank you.
Thank you, Dr. Rajat. It was a very informative lecture. So any queries from the participants? You can directly speak. So I have a small query, Dr. Rajat.
Yeah.
Actually, what the formation formation finds?
What?
How they cause the formation? What the formation find, and how they cause the formation damage?
Yeah. See what happens. See what we see. Suppose if I take this acidization job. Okay. So once when we are dissolving this say rock matrix, say sand carbonates or say sandstone or the cementation material. So once it is being dissolved by the acid, so where it will go? It will be there inside the formation only. So once we are not able to remove that particular generated fines up to the wellbore, or the wellbore cleanup is not efficient, so these fines, what happens when the pores which are connected, well connected, in the absence of these fines with the subsequent flow of fluid inside the reservoir, they will go and migrate and sit in that particular pores. And when these pores are being blocked or being settled by these particular fines, so what happens? The connectivity will be decreased. So the interconnectivity between the pores is being now disturbed with the presence of these fines. So we have this simple fundamental of the reservoir like shorting. So poor shorting and finer grain shorting. So all these things will affect the permeability. That's how they will contribute to damage. I think it is clear. Huh? You want me to explain more?
Okay. Yeah. Thank you. Thank you so much. Any other query? So I think there is none.
Okay, so
I'll give.
if someone has, they can directly send emails also. So it is there in website. You can check if there is a scope for some research or some collaboration that can also be done. So
Yeah.
that's from my side. Yeah.
Thank you so much. So I'll give the remarks now. So on behalf of everyone present in this program, I want to thank Dr. Rajat Jain for his informative and interesting presentation on the very important topic of well stimulation techniques. We appreciate you for sharing your knowledge and expertise. So your lecture touched upon so many critical areas related to well stimulation techniques like formation damage, their types, how they are caused, about the scales, the stimulation jobs like the acidizing in sandstone and carbonates, and also the different types of the acids and surfactants that are used. Once again, from all of us, thank you so much. Thank you, Dr.
Thank you.
Thank you so
Thank
much.
you, sir. Thank you. Thank you.
So we'll break for lunch now. Thank you everyone for attending the session. So please join me again at 3 p.m. for a talk on unconventional hydrocarbon ENP. So please join at 3 p.m.
This conference will now be recorded.
Hello everyone, welcome back. Now we shall begin the third session for today. So it gives me immense pleasure to introduce our resource person for this session, Dr. Himanshu Kakoti of IIP Vizag, who is going to talk on the topic of unconventional hydrocarbon exploration and production. Dr. Himanshu Kakoti is currently working as an assistant professor at Indian Institute of Petroleum and Energy, Vizag. He did his MTech in the Department of Petroleum Technology, Dibrugarh University, and PhD from IIT ISM Dhanbad, with gas hydrate as his research topic. He has more than 8 years of research and teaching experience. His research areas include gas hydrates, EOR, fracturing fluid. He has a number of international publications in SCI journals and conferences, presentation, invited talks to his credit. So please join me in welcoming Dr. Himanshu Kakoti. Over to you, Himanshu.
Thank you, sir. So, good afternoon, all participants, faculty members, and research scholars. First of all, I would like to thank Dibrugarh University, especially Ranjan Phukan sir, for giving me this opportunity to interact with you. So, today I'll give my presentation on this gas hydrate production from hydrate reservoir. So, here I'll discuss various techniques of gas production from hydrate reservoir along with their drawbacks and limitations. Along with I discuss various test field results so far conducted around the globe and their how we can analyze those data based on this data, how can we move forward, that part also I discussed after that. So when we look at this world energy consumption, this world energy consumption is increasing day by day, and obviously because of increasing population, because of increasing population, the energy demand required for to meet the day-to-day life requirement increases. So we need more and more energy. Also, as a human being, we need a higher standard of living. So we aspire for higher standard of living. So for to meet that demand, we require energy, and this energy comes from various sources like oil, natural gas, coal, hydroelectricity, renewables. But among that, if we look at these figures published by British Petroleum in their annual review, we can see that among all these energy source, oil followed by coal and natural gas provides the bulk amount of energy we require till now. And among these, the share of, if you look at the share of the global markets of different energies, oil continues to hold the largest share of around 33%, followed by coal 27%. This is the data in 2019, last year, where we can see there is a dip in the coal consumption. Because more and now actually coal is a very dirty you can say energy, where because when you burn coal, you combustion, because of the combustion of coal, the amount of greenhouse gas released to the atmosphere is too high compared to your natural gas or your oil. So more now the countries around the world are planning to decrease the consumption of coal, that is industrial application, and that's why you can see that there is a dip in the consumption of coal recently, in the recent last 5 years. Then you can see there is a increase in the this consumption of natural gas. So other hydroelectricity, nuclear, renewables are still at the initial state. We require more efficiency from those fuels. So when we look at the India's scenario, we can see that in India, the main source of energy is coming from coal, followed by your petroleum products, then biomass. Here we can see that natural gas, the amount of natural gas usage is only 6%. Now, when we look at this coal and petroleum these petroleum products, this, as I have told you, this releases the greenhouse gas compared to natural gas. Here we can see that carbon dioxide, one of the main source of greenhouse gas released to the atmosphere, is 60% around. So that is a huge amount. So now the countries are planning to reduce this emission, greenhouse gas emission to the atmosphere, so that it can reduce the global warming to some extent. But we cannot stop using this source of energy. I mean, we cannot stop using coal or stop using petroleum products unless and until we cannot discover an alternatives. So we have to find one alternative. Instead of, if you want to reduce the amount of consumption of coal, we have to find out an alternative, so that we can meet the energy demand. So one alternative can be your natural gas, because the natural gas, the consumption of natural gas produces very less amount of greenhouse gas. So natural gas is cleaner compared to your coal and your crude hydrocarbons. So when we talk about natural gas, the source of natural gas is mainly, as you know, you can produce natural gas from your conventional reserve. Conventional, that means sandstone reserve. We can produce from shale gas. We can produce from CBM, as well as we can produce from gas hydrate reserve also. And from this diagram, we can see that the amount of gas trapped in those methane hydrate reservoir is too huge, about 3000 TCM, compared to conventional gas 404 TCM and unconventional combining CBM, shale gas, and tight gas 664 TCM. So, however, if the amount is too big, however, the recoverable amount may be small, because when you look at this energy pyramid, at the top of the pyramid, the gas is stored in the sandstone, a poor spedia, where we can produce those gas easily. That means this energy we can produce efficiently. We have technologies available with us. But when we go downward in the energy pyramid, though the volume available, the gas available in those reserves is too big, but the technological advancement, or we cannot, at present we cannot think of producing this volume efficiently and economy. We don't have those technologies available. So, however, if we can produce the 10% of this gas also, minimum I am saying, then also it is almost equivalent to your conventional gas. So that's why gas hydrate can have the potential to be an alternative energy source if we can produce those gas stored in those reservoirs. So before going for the production, how to produce gas, we have to understand how gas exists in the hydrate reservoir. Then only we can produce it. So gas hydrate, so what is gas hydrate? It's a crystalline solid actually formed of water and gas, more like an ice-like structure, but gas are inside those ice crystals, and it exists in huge quantities naturally. We can find those hydrate in the reservoir in most of the marine environment, and as well as in permafrost reservoir also. So however, almost 95% reservoir are in marine sediments, and compared to 3% rest is in permafrost region. So when we keep the gas molecule and water under high pressure and low temperature condition, this water molecule will form some cage around those gas molecule. This cage is formed by this hydrogen bond. This water molecule is bonded with this molecule through hydrogen bonding, so it is forming a cage around this gas molecule, and this gas molecule is entrapped inside those gas or cavity. And however, there is no bonding between this gas molecule and water molecule, because the gas molecule is free to rotate inside this cavity. Generally, most of the hydrocarbon which can form gas hydrate are light hydrocarbon like methane, ethane, propane, carbon dioxide, because since gas is entrapped inside the case or cavity, so it's depend on the size also. Its size cannot be too high, otherwise it cannot accommodate inside this cavity. That's why only few certain gas can form hydrates. So among these is methane, ethane, propane, isobutane. Then other gases like hydrocarbon, nitrogen, H2S can also form hydrates. So as I have told you, the water molecule forms some cavity or case around the gas molecule, and gas molecule entrapped inside this cavity. So there are 5 types of cavities generally we noticed in gas hydrate structures. These cavities are dodecahedron, tetrachedecahedron, hexachedecahedron, irregular dodecahedron, and isocahedron. So dodecahedron, here 12 pentagonal face is there. This type of pentagonal face, 12 pentagonal face consist of in dodecahedron. In tetrachedecahedron, we have this pentagonal face, 12 pentagonal face, and 2 hexagonal face. Similarly, in hexachedecahedron, we have this pentagonal face, 12 in this structure, and we have 4 hexagonal structure in this structure. Like similarly, in these two structure, we'll have square, pentagonal, and hexagonal face is there. So these 5 cavities will form when you will keep hydrate, I mean gas molecule and water under favorable pressure and temperature. When I'm saying favorable, that is your high pressure and low temperature condition. However, we won't get all types of all these 5 cavities or 5 structure in all types of hydrates. Generally, we have 3 types of hydrates: cubic structure 2, and hexagonal structure. Cubic structure, and it depends on your the size of the gas molecule it can entrap or it can accommodate. When the size of the gas molecule is 4.2 to 6 angstrom, that forms your cubic structure 1, for example methane, ethane, carbon dioxide, hydrogen, etc. Then cubic structure 2 formed by molecule having diameter less than 4.2, size less than 4.2 like nitrogen, or size in between 6 to 7 like propane or isobutane. It can form cubic structure 3, and hexagonal structure H form when the size of the molecule is 7 to 9 angstrom in between. Above these cannot, above those molecule cannot form any hydrate structure. However, here in the hexagonal structure, like isopentane can form hexagonal structure because its size is in between 7 to 8 angstrom, but it cannot form hydrate alone. For example, when we keep methane and water at high pressure, low temperature, methane will form methane hydrate. But isopentane, though it is from hexagonal structure, it cannot form the hydrate alone. We have to keep some accompanying molecule. Accompanying molecule is methane, hydrogen sulfide, or nitrogen. That means when we keep isopentane with methane, then only we will get hexagonal structure formed by isopentane hydrate. Okay, this 3 structure is there. Generally, in when we are talking about mostly interested in the production purposes, then mostly available structure or most structure available in the this reservoir: cubic structure 1 and cubic structures 2. As I've told you, though we have 5 types of cavities, all 5 types of cavities you won't get in the every structure. For example, in structure 1, we'll get dodecahedron and tetrachydecahedron. 2 cavities of dodecahedron this cavity and 6 cavities of this. This will form structure 1 unit cell. Similarly, structure 2 unit cell, we will find this cavity dodecahedron and hexadecahedron. Here in structure 2 unit cell, we have 16 numbers of dodecahedron this cavity and 8 numbers of hexadecahedron this cavity. These 2 cavity will form 1 unit cell of structure 2. Similarly, in structure 8, we will get these 3 cavities for 1 unit cell of structure 8. Here we can notice here also 42 water molecule per unit cell, 136 molecule per unit cell, and 34 water molecule per unit cell. Here this unit cell indicates, the water molecule per unit cell indicates that when we think about producing structure 1 by dissociation or by some other method, so we have to deal with this water also, because this water will also produce. So when structure 2 is there, we will get higher amount of water compared to structure 1. Now the modern studies of gas hydrate aims at the following goals: prevention of formation of hydrate, and removal of, if formed, how to remove those hydrates efficiently. See, we are looking for hydrate reservoir to produce the gas, methane gas trapped there, so that we can use those methane as a source of energy. But when hydrate form during transportation, during processing or production equipment, during production inside the equipments, then that is a problem. No one wants the formation of hydrate plug inside drill pipe or inside BOP or inside pipelines, because imagine when suppose you are drilling somewhere and hydrate is formed inside the drill pipe. So as you know, it is a solid structure, isolated structure, so after some time it will block the flow of drilling fluid through the drill pipe. However, for continuous drilling you require continuous circulation of drill fluid, so obviously it is unwanted. Not only that, when hydrate forms means what? You have water and gas under favorable high pressure and low temperature condition. Now when hydrate forms, that means it is taking the water from the drilling fluid also. So when it is taking the water from the drilling fluid, it is changing the rheological properties of the drilling fluid, which is mostly unwanted. So obviously which may lead to other disaster also. So that's why think about formation of hydrate plug inside pipeline. If hydrate plug form inside the pipeline and it completely disrupt the flow, then you have to stop the flow, you have to use some pigging operation, you have to remove it, then only you can again use those pipeline for transportation purposes. So that means in whether it is production or transportation or processing system, the formation of hydrate inside any system equipment is unwanted. So how to prevent this formation, or if form, how to release or how to remove it, there is one aspect of hydrate study. Other is the exploitation of natural gas from those hydrate reservoir efficiently and economically, and along with the studying of this environmental impact of those exploitation methods. So in this presentation I will discuss mainly this aspect, this exploitation of natural gas and their impact on the environment. One other aspect is this industrial application of hydrate based technologies. We can use hydrate for storage and transportation purpose also, because you see hydrate is what it is a water structure inside which gas is present. So that means and it has been proved that 1 meter cube of hydrate can contain 160 times of methane gas under standard pressure and temperature condition if all cages are filled. So that means in a small volume you can accommodate huge quantities of gas. So it can use as a storage medium obviously, and also you can transport it, and it is relatively safe as uh, uh, the release of gas will only happen when you disturb the the temperature and thermodynamic condition, pressure and temperature only. Unless and until temperature and pressure is within your hydrate stability zone, there won't be any leakage problem, gas leakage problem. So it is completely safe compared to the other mode of transportation. Also, you can use the desalination, that means removal of salt from the water. Also you can use the hydrate based technology for separation of gas also. Anyway, I am not discussing all this in this lecture. I will discuss only the exploitation, the second aspect, exploitation of natural gas hydrate only. So this is the map of gas hydrate discovered around the world. As you notice, most of the gas hydrate is in the offshore region. Yeah, this is the India, this KGB seen in Andaman, where in India discovered gas hydrate in the coast of Japan as well as South China Sea, then Gulf of Mexico. But here in this Tibetan region in China, they have discovered hydrate in the permafrost. Here also Alaska permafrost region. So, but however, you will see most of the gas around, as I have told, most of the 97% around world reservoir in uh, marine environment compared to few in the permafrost region. So, in marine setting, generally in the continental slope, this slope in this zone, most of the hydrate exist as the because for the existence of hydrate, we require the pressure and we require suitable pressure and temperature condition also. And in this slope region, the pressure and temperature is ideal for the formation of hydrate. So most of the hydrate reserve exists in the marine environment in the continental margin. Similarly, in the permafrost region, we will get the hydrate below this ice layer. So next, gas hydrate petroleum system. For any commercial production from any conventional reservoir, we have to find out the petroleum system. where conventional petroleum system component of a petroleum conventional system is your source lock, migration pathways, sedimentary lock, cap rock, etc. So if this all the components are there, all the components of petroleum system are there in a conventional reservoir, then only we can go for we can plan for extraction of those hydrocarbon from this conventional reservoir. Similarly, in the gas-headed reservoir also, the gas-headed petroleum system consists of, or the component of gas-headed petroleum system is gas-headed stability condition. That means you have proper temperature and pressure condition. That means high pressure and low temperature condition should be there in the reservoir. Then gas chemistry, type of gas, because you have noticed that gas molecule above 9 angstrom cannot form any hydrate structure, and below this also 9 angstrom also, depending on the size, different types of hydrate forms, and different types of hydrate is associated with different types of structure. Different types of structure means different types of water molecule and all these things. So gas chemistry, that means that will also we have to determine pore water salinity, because reservoir condition like salinity, then capillary size of capillary of the reserve this porous media also affects the uh, pressure temperature condition. So gas headed stability condition is one thing required for the gas headed petroleum system. Then is source of gas, availability of the gas. Source of gas may be your biogenic gas or thermogenic gas. When biogenic gas, this is biological origin because of the decay of bacteria. So at this biogenic gas you will get at the shallower depth, and compared to the thermodynamic, where thermal degradation because of the temperature. But thermodynamic gas generally exists at the deeper zone. Deeper zone means high temperature region zone. But one thing you can notice here is that gas headed generally exists at the shallower depth, because for gas headed stability condition, to satisfy the gas headed stability condition, that is the formation temperature required is less. It cannot exist at high formation temperature. So generally when you go deeper, formation temperature increases, but thermogenic gas exists at the deeper zone only because of it required a thermal degradation. So for any thermogenic gas like that, the gas mass has to travel from its or migrate from its origin to the upper level through some fracture or some channeling, so that this thermodynamic gas reach the proper pressure and temperature condition to form the gas. However, biogenic gas, there is no such condition, because biogenic gas form at the shallower depth. So and shallower depth is the suitable for, mostly suitable for hydrate formation and formation condition. And when biogenic gas, mostly methane, and in thermodynamic gas, so we'll get along with methane other component may also present like propane or ethane. Generally when methane and ethane is there, structure 1 hydrate will form, and when propane is there, it will form structure 2 hydrate. Third component of petroleum system is availability of the water. For the formation of, obviously, though we have gas, if there is no pore water in the inside the pores, then hydrate cannot form, though the pressure and temperature condition is within that stable region. So we must require the water in the pores media, which is obviously available, mostly available in the pore space. However, we have to, depending on the salinity, this pressure and this salinity, this pressure and temperature condition may changes. Then migration of gas within the hydrate structure. For the production, for any hydrate structure, say for example repressurization or any hydrate structure, we require some effective permeability in the porous media also, because our pressure has to move through this porous media. Pressure disturbance has to move, or pressure response has to move through the porous media. If 100% saturation, gas saturation is the 100% saturation means all the pore space is completely filled with hydrate, and when hydrate means the solid structure, that means all the pore space is filled with solid structure. That means effective permeability for other phases is completely zero. So in such cases, you cannot think of producing those structure, because you don't have any permeability for other phases. water or your gas mainly. Then as conventional, we require rock, porous media, trap and seal also. So this is the phase envelope diagram for gas hydrate structure in marine sediments. So marine sediments, this is the water depth, this is the depth. This depth indicate one way is the pressure, increase in the pressure level, and this is the temperature axis. This is your hydrothermal gradient in the sea water. This is your sea floor, and this is your geothermal gradient. The pressure increases. So this is the phase envelope. So from this intersection 2 point, this is the sea floor, and this is the intersection of hydrothermal and your phase envelope. So this is the zone. This is the zone where we will get hydrate at the marine sediment. That is your 1200 to 15, around 1600. So this is the thickness of hydrate in the marine environment based on the phase boundary and your hydrothermal gradient. Because below this hydrate cannot exist because temperature is too high. Similarly, here in the this is the phase envelope for permafrost region, where this is the geothermal gradient in the permafrost. This is the depth of permafrost, and this is the your pore space where hydrate can exist, porous media, and this is the geothermal gradient. This is the intersection of this phase envelope and geothermal gradient. Below this, hydrate cannot exist because of the higher temperature. This is the zone where hydrate can exist in this temperature -10°. This is the temperature region, and this is the thickness. Thickness, as I have told you, thickness we can convert it to pressure. Mainly, is the existence. This envelope is mainly depends on your pressure and temperature condition only. As also obviously affected by your salinity and pore space. That is different. But if you compare with the simple water, no zero salinity water, this envelope we can generate based on the pressure and temperature response, and when we pressure we convert it to the depth, we will get this profile, and from here we can find that the depth from 600 to around 11-1200 we will get this hydrate in the permafrost region. So we will get hydrate reservoir in nature as shallow gas deposit as well as deeper gas reservoir. When we are talking about shallow gas deposit, shallow means that means you can see here this is the sea floor and this is the hydrate zones. That means hydrate can exist at the sea floor also. Is it or not? When hydrate exists at this near at the sea floor, that are the shallow gas. But from that you can say the sea floor is mainly unconsolidated sand. So when unconsolidated sand hydrate is formed inside the unconsolidated, you will get some this bulk deposit. Instead of inside porous media, this shallow deposit is mainly this type of bulk deposits or some layer type, because it's unconsolidated formation. The hydrate, when hydrate form, it displaces the sand grains. As a result, you will get this layer type or this bulk deposit, or even in the outcrop you can see from the sea floor also this type of hydrate outcrop at the sea floor. So obviously from commercial production point of view, there is no scope, or you can say there is no technology available till now where we can produce those hydrate. So when you can go back to that slide where I shown you this gas hydrate energy pyramid. So in the gas hydrate energy pyramid, this hydrate deposit, this shallow gas hydrate deposit is at the bottom of the pyramid. That means volume is too high, but there is no technology, or we cannot produce those gas efficiently or economically. So this type of hydrate, shallow gas hydrate, has been found in Gulf of Mexico, Caspian Sea, Black Sea, this marine setting, and since it is a shallow gas reservoir, mainly biogenic origin gas are there. So structure 1. However, in Buckley Canyon, they have found thermogenic hydrate also at shallow depth 2. That means it must be traveled, or is migrated from the source to this shallow depth from through some fracture in Buckley Canyon. That's why they are getting this hydrate, thermogenic hydrate at shallow depth. Now deeper gas deposit, but see, don't get confused when I'm saying deeper. it cannot be goes below this baseline, because below this hydrate cannot be. When I'm saying deeper, that means deeper means this region, around this region. So in deeper hydrates, we'll have pore filling types or load bearing types or cementing. In pore filling types, hydrate nucleate here, then grow in the pore space, and then it filled up the space. So mostly this type of reservoir are best candidate for production of gas from this hydrate reservoir, because generally uh, this hydrate we require a stable structure also, because these are stable structures. However, one thing you have to remember here is that since hydrate is growing inside this pore space, so this saturation should not be 100%. As I've told you earlier also, we require some effective permeability for movement of other phase also. Then here in load bearing type, what happen? Hydrate initially grow inside the pore space like this one. Then it grows in volume and it displays the sand grains. When it displays the sand grains, and it becomes a part of the structure also. So it carries the overburden of this formation. So it becomes load bearing hydrate. It's called the load bearing hydrate structures. Then hydrate can form in between the two grain particle and it can cement it. So out of this, as I have told you, this is the pore filling hydrate are the most sought hydrate for commercial production from hydrate reservoir. Because see, you can if load bearing structure is there, and if you dissociate this hydrate, when you have to produce, you have to dissociate it. When you dissociate the hydrate, there might be a chance that the formation may collapse, because this hydrate gain is taking the load of the formation. When you dissociate it, it becomes water and gas, and when it becomes water and gas, it is no longer taking the overburden pressure. So yeah, there might be a chance of getting collapsed here. So this is the best candidate for commercial production. So pore filling hydrates. So in pore filling hydrates, you will get these different types in the actual reservoir condition, where pore filling, or if the pores grain is there, mainly there is sand and gravel is there, then we have perfect pore filling, where hydrate goes inside the pore space here. But when we have clay and silt is there along with sand, then we may get this nodular type or this fracture type, where in fracture type, hydrate exists in the fracture along with the pore space, and here in this case hydrate exists in nodular types. So again, if the pore filling type of this having coarse grain structure is there, these are the again base candidate. That means among the pore filling reservoir also, if hydrate exists inside the pore space only, and that happens when we have coarse grain, then the size of the grain is more than your clay or silt. That means when we have gravel and sand is there, then coarse grain this, then we have pore filling, completely pore filling. Fracture type, however, in India, offshore India, the reservoir, most of the reservoir, hydrate reservoir is this fracture type, along with this pore filling also there. However, but mostly these are this fracture type reservoir. So pore filling reservoir, we can differentiate again. Pore filling reservoir differentiate into 4 categories of hydrate reservoir. This one is class 1, then class 2, class 3, class 4. Class 1 is, this is sediments, caprock, this is impermeable layer. Below is your hydrate reservoir, then below is your gas layer in water. So the gas in the water indicates that this is outside the hydrate stability zone. That means pressure and temperature in this zone is not suitable enough to form the hydrates. That's why we have free water and free gas here. And this is your class 1 reservoir. This is the base reservoir to produce, because one of the production method is to depressurize. That means we have to decrease the pressure of the reservoir. And here in this type of class 1 reservoir, when we produce from this zone this free gas, then automatically the pressure in this reservoir decreases. So that means by producing the free gas from this zone, we can decrease the pressure in this zone and pressure in the reservoir, and ultimately we can dissociate the gas added from this zone also, and we can produce the gas and trap here. So this is one of the, I mean, best reservoir, gas added reservoir, you can say, for commercial perspective. Then class 2 reservoir is hydrate below or underlined by only water, there is no gas is there. Here in this case also you can decrease the you can produce the water and decrease the pressure. However, when you produce water, you have to think about disposing it and purifying it also, because you cannot dispose it anywhere. And while disposing of this water, produced water in marine environment, it is a costly affairs. So you have to think about in producing more and more water to decrease the pressure in hydrate reservoir in this type of class 2. And class 3 reservoir, both we have this impermeable layer, and in between these two impermeable layer we will have hydrate reservoir, hydrate in the pore space. In this case you have to use some pumping method, you have to use some pump, ESP or some other jet pump like this in the wellbore to decrease the pressure for the production in class 3 type. Then class 4, this is the hydrate nodule structure, nodular like structure dispersed in the reservoir. And obviously this type is people are not looking for this type of structure, as this is not so efficient. First of all, not efficient, this is not huge quantities, not getting any waste quantities. Also we don't have those technologies available right now. So again you can place this class 4 structure in the bottom of this hydrate pyramid. So class 1 reservoir, when we look at this worldwide scenario, this Russia and in Alaska, they have class 1 reservoir. That means gas is there below the hydrate reservoir. Class 2 reservoir is mostly a part of eastern Nankai Throw and Malik Field. Class 3 reservoir is most of the Malik Field, Nankai Throw. Then this Mount Alberta are categorized in this class 3 reservoir. That means entrapped both sides by both overline and underline by impermeable formation. Then class 4 also, they are low saturation, so not much data is available because no, most of these are not looking for this type of reservoir. Now for production of hydrate, see, when we have to in conventional reservoir, for production we have to drill a well, then we have to establish a drawdown, and because of the drawdown the hydrocarbon moves towards the wellbore and we can produce it. I am talking the most simpler one, I'm not going into complexities, but the most simplest method is that. But in gas hydrate, to produce, we have to first release the gas from the hydrate structure, because hydrate structure, gas is inside the water case. That means we have to first dissociate, we have to first take out the gas molecule from the water case or water structure, then only we can produce. So for production of water case, that means we have to destabilize the hydrate. So how to destabilize the hydrate? There are a few methods. For example, say this is the phase diagram, this is the gas hydrate phase diagram. This phase diagram indicates this is the region where the pressure and temperature condition is such that hydrate is stable. That means gas hydrate is stable, means gas molecule within your case formed by the water molecule, and this is the region, this phase diagram. So below this phase diagram, this is the region where is unstable region. So if gas hydrate reservoir is that means gas headed reservoir means that is above this region, above this curve. So I have to bring this pressure and temperature condition or reservoir condition from this to below this curve, this hydrate phase equilibrium curve. This can be done by this way. This way means decreasing pressure, that is called depressurization, or I can go this way. This way means increasing temperature, that is called your thermal method, and this is inhibitors I will discuss later. So that means we have to know this phase equilibrium diagram, this phase equilibrium curve for each reservoir, so that we can plan accordingly how much pressure we have to drop or how much temperature I have to increase. So this phase equilibrium curve we have to decide. So this is the phase equilibrium condition of different gas hydrate. This is the phase equilibrium curve for methane. That means methane is stable here. Below this is the region where methane is unstable. Similarly for ethane, this is the region where ethane is stable. Ethane hydrate will get at this pressure and temperature condition. This is the region where methane hydrate is unstable. Similarly for propane and butane. So this is for pure methane hydrate, for pure butane. If there is a mixture is there, then phase equilibrium curve will be in between these two limit. Okay. However, this phase equilibrium, this phase diagram or phase equilibrium is affected by reservoir condition. Reservoir condition means affected by salinity. Different reservoir has different salinity. Affected by capillary size of capillary or sand grain structure, or gas composition. Different reservoir has different gas composition. Some has biogenic origin, so methane is only there. Some has if the thermogenic gas having propane is there, then the phase diagram will change. So that's why this is the effect of gas molecule on the hydrate diagram. Here we can see this methane hydrate. This is the methane hydrate forming at high pressure compared to this propane hydrate, pure propane hydrate forming at low pressure compared to this methane hydrate. And when we have 95% methane and 0.5% propane, the curve will shift towards this direction. Only 5% can. So that means different gas molecule also affects this hydrate phase diagram. Generally, propane, when propane will there, will get the hydrate at milder condition. Milder condition means less pressure and higher temperature condition, because the size of the propane is such that it can fit inside the gas molecule too easily and without any disturbances. So when propane is there, it quickly form the S2 structure easily, because it quickly accommodate inside this cavity. That's why it forms at the very low pressure, not very low pressure, but low pressure compared to methane. So that means when we think about depressurization, if methane hydrate is there, we can think about depressurization from initial condition is here at this region to here only. We can depressurize it. But for when we have propane is there, that means structure 2 is there, we have thermogenic gas origin is there, then we have to depressurize below this curve to dissociate the hydrate in the reservoir. And salinity also affect, because pore space always contain your water, and water may be water may have various salinity. Based on the salinity value also, this phase equilibrium curve changes. This is the pure water. When we add 2% sodium chloride, this curve move upward. When we increases the salt content, it moves again towards the high pressure zone. That means when salt is there compared to fresh water, hydrate will form at a high pressure condition, and most of the pore fluid contains the various amount of solvent. Based on that, we have to determine this phase diagram, so that we can bring this reservoir condition outside this phase diagram, that is below this phase diagram. Then also size of this grain size also affects this hydrate phase equilibrium diagram, hydrate pressure and temperature condition. This is the bulk phase, that means in without any porous media, when pore size increases, the smallest porous media formed as a high pressure. So when we have small grains, the small grain, that means clay silt is there, the hydrate will form at high pressure, and when we have sand, that coarser grain is there, then we have form at lower pressure compared to your silt and shell. That means this size of this grain particle also affects the hydrate pressure and temperature conditions. Other than that, other component like these minerals also may affect your pressure and temperature condition. However, these are the three main conditions: this gas component, salinity, and this size grain, which affect the pressure and compressor condition phase diagram. So before production or any reservoir, we have to find out this phase diagram for each and every reservoir before planning for any type of depressurization or thermal or any type of production technique. So we have four methods of production currently: depressurization, then thermal, inhibitors, and methane. As I have told you, depressurization is we have to reduce the pressure of the reservoir so that the pressure goes below the phase or equilibrium pressure. So this can be done by removing the free gas in class 1 reservoir, because in class 1 reservoir we have below hydrate, we have free gas is there. By removing those free gas, we can decrease the pressure, or in class 2 we can decrease by removing the water from those underlying this underlying layer below the hydrate. We can remove those water from those layer, and we can decrease the pressure in that reservoir, or we can install some pump, ESP or something like that in class 3, where both this hydrate layer is entrapped between these two impermeable layer. So when we decrease the pressure, so hydrate will dissociate, and when hydrate will dissociate means it will release the gas molecule, and when it will release the gas molecule you can produce here. However, along with the gas molecule, water will also come, and when hydrate is dissociating means permeability is increasing. Why permeability is increasing? Because see, hydrate is when hydrate is dissociating means the saturation of hydrate inside the pore media decreases, and hydrate is generally solid one, and solid type structure. So when hydrate form inside this porous media, that means effective permeability for other medium is less. But when you dissociate it, when it become water and oil, so in dissociated zone, you will get higher permeability. And when we have higher permeability, this pressure disturbance, or this when you have this pressure disturbance will move faster rate, because you know the radius of investigation is directly proportional to the permeability. So once you have this higher permeable zone, this radius of investigation moves towards this direction, and that's why will dramatic permeability increase in the methane hydrate zone, and as a result you have much better pressure transfer occurs, and when much better pressure transfer occur, you will get the dissociated hydrate. You can dissociate the hydrate like this. Pressure will moves in this direction, pressure, and then keep on dissociating the hydrate. However, one time will come when it will stop, because see, this is the initial condition, okay, above the hydrate phase equilibrium curve. Now you depressurize. Depressurize means decreases the pressure, and when you depressurize the pressure, hydrates are dissociating. Generally, hydrate dissociation is a endothermic reaction. Endothermic reaction means heat is being taken from this surrounding media. So that's why during the dissociation process or depressurization process, this surrounding media become cooler and cooler. Cooler and cooler means what? The temperature decreases. So when during this depressurization, temperature decreases means one time will come when temperature will reach this three-phase temperature diagram. Phase diagram at this temperature, that means hydrate will stop dissociating, because we have to goes below this phase diagram, then only you can dissociate it. So in this case, however, when temperature reach here, because of the endothermic reaction, after reaching the temperature here, at this point the dissociation continues but at slow rate, because because heat is being taken from this overburden and underburden region. See, this region, because of the dissociation happens in this region. So as dissociation occurs because of the endothermic reaction, in this zone temperature will be less. So now temperature in this underburden and overburden region will high. So this temperature flow or heat flow occurs from this zone. So because of this heat transfer, you will get when temperature is high, because of this heat transfer, dissociation will keep on going, but like this you will get a temperature in this zone will be high, so hydrate will dissociate like this. At this zone hydrate will dissociate, but central portion it will remain. So in this production test, already depressor method was done in Malik production in April, and I will discuss this later. And next is your thermal method. Thermal method is simple as like your UR, thermal stimulation or thermal flooding. Thermal stimulation method includes hot water circulation, where you will inject the hot water in the wellbore, and it will be taken by this formation. As a result, this hydrate will dissociate. As a result, temperature increases. Temperature increases. When temperature increases, hydrate stability zone goes outside the pressure and temperature, stable pressure and temperature. As a result, hydrate will dissociate. However, in hot water circulation method, you have to remember one thing, that you have to inject you have to inject the water. So inject water means you have to inject water at the pressure greater than the initial pressure. And when hydrate is there means the pressure in the reservoir is obviously high pressure, because hydrate form only when form preferably in the high pressure and low temperature zone. So the reservoir where hydrate you will get generally high pressure reservoir. So high pressure reservoir is there and you are injecting water, so you have to your injection pressure should be greater than the initial reservoir pressure. And greater injection pressure means you require high pressure rating equipment at the surface. So those you have to take care. Similarly, thermal flooding. Thermal flooding here, what this means, you are injecting thermal means you are injecting hot water here, and you are producing from the other well in a distant in a separate well here. But again, the feasibility of this project depends upon the effective permeability ones, because water has to move through the porous media. Second thing is that when water is moving, suppose say you are injecting hot water is moving here. So when water reaches here, that means this is the dissociation zone. Dissociation zone means hydrate dissociated here, because of the endothermic reaction, this become cooler region. Now when water reaches here, and hydrate may reform here, because endothermic reaction, your hydrate is your temperature become too cool here, and already you are injecting at a pressure, so pressure is already there, so there might be a formation of hydrate reformation in this zone. And once hydrate will reform in this zone, it will block the injection of flooding. So these difficulties are there in this type of this thermal project. However, it is one of the least efficient method of producing. Another method is your inhibitor injection. In inhibitor injection, what we'll do, you can see here, this is the phase equilibrium diagram. The initial pressure and temperature condition is above this phase equilibrium diagram. So in depressurization and thermal flooding, we bring this equilibrium condition, this initial pressure condition, outside this or below this curve by reducing pressure on this. We can achieve the same objective by moving this phase equilibrium curve in upward direction, so that this initial condition of hydrate reservoir automatically come below this phase equilibrium curve, and this can be achieved by injection of inhibitors, thermal inhibitors. So when we inject thermal inhibitors, it shifts the phase equilibrium curve towards high pressure region, and when it shifts towards high pressure region, the initial condition, pressure temperature condition automatically come outside the hardest stable region, and when it is outside the hardest stable region, so it starts dissociating. However, when we talk about the inhibitors, so we have to remember that we have three types of inhibitors is there. One is thermodynamic inhibitors, where it affects the pressure and temperature condition, and other one is low doses low doses hydrate inhibitors, where we have kinetic inhibitors and anti-agglomerants. Here, these kinetic inhibitors and anti-agglomerants cannot affect the pressure and temperature condition. These kinetic inhibitors only affect the induction time, and anti-agglomerants prevent the agglomeration of hydrate particle only. So this kinetic inhibitor in the induction time means when we will keep water and gas at hydrate forming temperature, it won't form hydrate immediately. It will take some time. After some time, only they will form hydrate, though the water and gas are inside the hydrate stable zone. This time required is called induction time. So kinetic inhibitor increases this induction time only, but it does not affect the pressure temperature condition. So these two inhibitors are mainly used for this prevention of hydrate formation in even drilling fluid or in pipeline only. For inhibitor injection, we only use thermodynamic inhibitor because these only can affect the pressure and temperature condition. So because we have to shift the pressure equilibrium towards the high pressure region, and it can be achieved only thermodynamic inhibitors only. These two inhibitors cannot be used for injection purposes here, for production purposes. So out of the thermodynamic inhibitors, we have DG diethanyl glycol, then this salt. These are thermodynamic emitters. Generally what happen, these thermodynamic emitters is, for example, glycol or salt. When glycol is added, this OH functional group attaches with the water molecule, and as a result the water availability for hydrate formation decreases. So activity of the water decreases. So when activity of the water decreases, so hydrate forms at high pressure, because that is why we require higher pressure for the hydrate. Similarly, salt, when salt is there, it ionizes in the water and it forms this ionic bond with the water molecule, salt molecule. So ionic bond is stronger than hydrogen bonding. In water gas hydrate structure, water molecule is forming hydrogen bonding among themselves, but those water molecules which are associated with salt, or which are in ionic bonding with salt, those are not available for hydrate formation. So as a result, we require higher pressure. That's why in this way the salt can affect the hydrate formation. That's why when salt is there, or glycol is there, or diethylene glycol is there, these thermodynamic inhibitor, they can they can affect the pressure and temperature condition. However, in these three methods, we have few drawbacks is also there. Like one drawback is hydrate reformation, as I have already told. Because of the endothermic reaction, the formation become too cool or too colder. As a result, and too cold or less low temperature is highly favorable condition for hydrate formation. Also, one is a memory effect. Generally, what happens when you dissociate hydrate, the water molecule retain the memory of the hydrate. So next time when it comes under pressure and temperature conditions slightly above also, slightly milder than the previous one also, then also it will form because of the earlier memory. So because of memory as well as endothermic hydrate dissociation, the hydrate reformation inside the pores media as well as inside the your this production facilities, that also is one major problem we have to think about in this three method: depressurization, thermal, and this inhibitors. Then water production and disposal. As as you can see in my earlier slide, uh, in structure 145 molecule per unit cell, in structure 2 138 molecule of water per unit cell. That means when you dissociate it, structure 1 hydrate 45 molecule produces 38 molecule. That means 85, minimum 85% water dissociation will produce when you dissociate it, either by depressurization or by your thermal or by injection. That means minimum 85% water you have to handle. And while I am talking about handling, that means you have to dispose. When those produce water, you have to dispose by following the rules and regulations set up by the government agencies. As well as if you are thinking about this injection also, you have to maintain the proper salinity before injection. So it's a costly affair. That means. Also, sand production is a huge problem, and you have to think about, one has to think about this controlling the sand in a proper and efficient way before this going for a commercial production. Then thermal injection, one difficulty is obviously energy requirement is too high for hot water or this transferring the steam. Then inhibitor injection, one difficulty is your low effective permeability, since solid hydrate is there, so effective permeability is already low, so you have to inject a chemical, so you require high permeable region. But since hydrate is itself is forming inside it, so low permeable region, these are mostly. And also you are injecting chemical and thermal inhibitor generally works at a very high concentration, around 50-60 concentration. So you require that percentage, that high concentration of your chemical, so it involves cost, as well as there are other aspect is this leakage to some other, since it is a low, I mean shallow reservoir, mostly other reservoir, there is a chance of getting this leakage to the drinking water zone. Other this problem is also there, so we have to think about before applying any of this method. So one last method, one is that methane and carbon dioxide swapping method. Here in this method, or here you can see that this is your methane reservoir, phase diagram of methane hydrate, this blue line. That means methane hydrate is stable in this zone, and below methane hydrate is not stable. Then this is the phase diagram of carbon dioxide. That means it indicates this is the zone where carbon dioxide hydrate is stable, and below this red curve, this is the zone unstable zone. That means here carbon dioxide is unstable. Now hydrate reservoir means somewhere here in this zone above this methane hydrate reservoir. Now if you decrease the pressure temperature condition from here, this position to this position, so at this position methane hydrate cannot form because it is below this methane hydrate stability curve. But this position, at this position, is above the carbon dioxide stability zone. That means carbon dioxide hydrate can form. That means if you can bring the initial condition from here, this zone, to in this zone, you can dissociate the methane hydrate, but at the same time you can form the carbon dioxide hydrate here. As a result, what will happen? The water production problem can be somehow managed, because when carbon dioxide will form, water will getting engaged with the carbon dioxide hydrate. So water product, you can, by this method you can reduce the water production. Also you can sequester carbon dioxide in the reservoir condition also. That means in one method you can serve two purposes: producing methane from the gas-heated reservoir. At the same time you can store carbon dioxide, which is one of the greenhouse gas. You can store, instead of releasing it to the atmosphere, you can store it in the gas formation. So what will happen when you inject carbon dioxide in the methane hydrate reservoir? It decreases methane hydrate reservoir. It decreases the, or it stability condition. It removes the stability condition. At the stability condition comes below this methane hydrate curve. As a result, methane hydrate will dissociate. Now you can see from here both methane and carbon dioxide form structure 1 hydrate. You can remember from here, structure 1 hydrate contains 2 cavities of dodecahedron and 6 cavities of tetrahedron, and structure 2 is this 16 cavities of dodecahedron, this cavity, and 8 cavities of this. Now both methane and carbon dioxide form structure 1. That means it has 2 cavities of dodecahedron and 6 cavities of this. This can be found from this ratio of gas molecule to the host cavity. That means as I have told you, only few molecule can form hydrate, and this depends on one aspect is the gas ratio, gas diameter. That means the gas molecule diameter by the cavity diameter should be in between 0.76 to 1. If it is less than 0.76, that means gas molecule is too small, and when it is gas molecule is too small gas molecule cannot stabilize the hydrate structure. It will if it gets entered inside this form, it will dissociate. It cannot form a stable structure. And if this gas molecule structure is more than one, that means gas molecule structure is greater than cavity, it cannot accommodate. So this is the criteria for stable gas hydrate structure, 0.76 to 1. Now from here you can see here methane. This methane molecule in structure 1 and structure 2. Structure 1 2 cavities is there, as you know. Structure 2 2 cavities is there. Here you can see in structure 1 this ratio is around 86 and structure 2 0.75. And in structure 2 small cavity 0.86 and 0.65. So that means from here you can see that methane can be accommodated in structure 1 of smaller cavity this because of H6 ratio is in between, as well as in structure 2 in this cavity again because of this favorable ratio. However, methane will ultimately form structure 1 because of the additional stability given by this 0.75. 0.75 is almost equivalent, almost near to 0.76. So methane in this cavity and in this cavity both gives the better stability compared to this, because here whatever methane enters in this cavity that won't be stable because of too low this ratio. This ratio is around 0.65 for methane. That's why methane will form structure 1 hydrate. Similarly, carbon dioxide can form C. Carbon dioxide cannot enter here, and out of these two cavity, this cavity and this cavity, it will prefer this cavity because of higher ratio, and it cannot enter in this. So carbon dioxide will form structure 1 and it will go to this cavity. And you remember one thing here in structure 1 we have both cavities, and when you compare the size of the cavity, this cavity is smaller than this cavity. That means this is larger cavity. Here also this one is larger cavity. So when I am saying methane can enter this small cavity, that means it can enter the large cavity also. But carbon dioxide can enter this cavity. It cannot enter this cavity because this cavity ratio is more than 1. Now see, in this case, both methane and structure 1. So when you inject carbon dioxide into the reservoir, it will destabilize the methane structure. Destabilize the methane structure. When it destabilizes the methane structure, methane will come out from the water molecule. And when methane will come out of the cases, carbon dioxide will enter this cavity. However, from this chart, you can freeze gas molecule the cavity. You can notice that carbon dioxide cannot enter this smaller cavity. Carbon dioxide can only enter this cavity. So when you inject carbon dioxide into a methane reservoir, the methane stability condition will be disturbed. As a result, methane will come out from this cavity and carbon dioxide will enter into this cavity. However, methane will remain in the small cavity, and as a result, you can produce the methane stored in those large cavity. However, since the ratio of small cavity, this cavity by this cavity in structure 1 is 2:1, that means 1:3. The efficiency of this process can be around 66% theoretically. This in terms of heat requirement, this process in terms of heat requirements is also self-sustainable, because the formation of hydrate formation is an exothermic reaction and hydrate dissociation is an endothermic. That means during the hydrate formation, carbon dioxide formation, this mass 57.98 kilojoule per mole, this mass of amount will be released, and endothermic, and this heat released during this carbon dioxide formation is utilized in dissociating the further methane hydrate, and methane hydrate dissociation only require 54.49. This is less than this amount. So this amount, whatever heat released here during carbon dioxide formation, can be utilized for the formation of for the dissociation of methane later. In this way, this reaction is self-sustainable also. However, the efficiency of this process can be improved by addition of nitrogen also, because as you know, as I have told you, because of the injection of carbon dioxide can remove the methane molecule from this cavity also, this cavity only. So because methane carbon dioxide cannot enter here, so the efficiency is maximum 66%. But when you use nitrogen also along with carbon dioxide, then carbon, since size of the nitrogen is smaller, and it can enter in this cavity also, this dodecahedron also. So that means it can remove the methane inside from this cavity also. As a result, by injecting carbon dioxide, methane, nitrogen, we can get better efficiency compared to only single gas molecule. And also this carbon dioxide, nitrogen is nothing but flue gas released by this all the industry in the atmosphere. So if we can inject those gas in this hydrate formation, we can produce it at the same way. We can reduce the emission of this flue gas into this in our environment also. So advantages is, obviously one advantage is water production will reduce, because in this case, since carbon dioxide hydrate is also forming carbon dioxide nitrogen hydrate, so water will get involved in the hydrate formation, so less amount. So geomechanical stability in depressurization or in other methods, you have we are since you are dissociating it means if it is a load bearing hydrate, if you are load bearing means you are dissociating the hydrate, so that might cause the wellbore collapse, or even the structural collapse may also happen in case of offshore. So in such cases, but here since you are not dissociating the hydrate completely, so the mechanical stability of the hydrate bearing sediment retained. Also plugging needed wellbore can be minimized, because there is no, the heat released, heat released during your formation, carbon dioxide formation is being utilized by the dissociation process. So there is no, colder region in the reservoir. So that way plugging near wellbore also can be avoided. So these are few reservoirs where the pilot testing has been already done. So one side is Malik side, where we have structured one hydrate is there, because most of the gases are only more than 99% gases is your methane. Here sand dominated, porosity 30, hydrate saturation is up to 90%, and effective permeability is 0.1 to 1 MB. So here effective permeability is slightly lower side here. Then Nankai throws Japan, here again structure one, fine here clay and seal environment. Here hydrate is 80% saturation. 80% saturation means effective permeability is high compared to this 90% saturation, because when you when hydrate saturation is more, we have less permeability. Though hydrate higher saturation indicate that we will have more gas, but we require some permeability for other phases also. So this is one of the good reservoir for production, since we have both effective permeability and high hydrate saturation. Here in the China, South China Sea, here propane is there. See, propane is there, so we will have this structure to hydrate is there. Here hydrate saturation is less, so effective permeability is also high. Then here again in China, in this permafrost region, they are again reporting this 66% of around 66 to 99% of methane. So they are getting the other gases are also there. That means so other gases is there. So that's why they are getting the structure to hydrate also. Then in Krishna Godavari in India, we have this structured one hydrate having mainly methane only, coarse grain, but in fracture formation, this saturation is very good, around 85%. So effective permeability is also high. Good for production purposes. So this is the summary. I will come back to later. So this is gas production from Malik field. In 1998, first oil drilled to evaluate these properties. Lithology already I have mentioned here. So first production in Malik field started in 2002. The method of production was thermal simulation. They have produced for 124 hours. Total gas production was 462 meter cube. Here they have noticed that there is too high sand problem as well as water problem. So the efficiency was not quite that good. So later in 2007 and 8, they again in the same formation in different well, they again conducted two experiments in 2007 and 2008 by depressurization. This time they produced by depressurization method. Duration was this in 2007. duration was 60 hours, but because of the irregular pumping operation, they use some ESP pump to decrease the pressure. However, because of the sand problem, they could not get this continuous pumping. They have to stop the pumping operation frequently. As a result, they're getting less production, and the pumping problem is because of the sand deposited inside the pump. As a result, they have to replace and they have to install it. So they could not get the continuous production. So total production was around 830 meter cube. Water production was 20. Efficiency of depressurization. They have calculated the efficiency. That means amount of gas produced. The heating value of amount of gas produced divided by the energy utilized, energy spent for running the pump at 40%, assuming 40% efficiency of pump. So this gave 10 times greater than the consumed current. That means 10% efficiency. And in 2018 they did it again for 6 days. However, this time instead of continuously removing the pressure, bottom hole pressure, they did it in a stepwise manner and use some screen to control the sand. Now this time they're getting higher production of gas, and water production is 70 meter. Efficiency also increases since getting higher production. So one observation you can get it from here. Instead of decreasing the pressure or reducing the wellbore pressure too high at once, you can go for stepwise reduction, which may give good efficiency. However, sand problem is there, sand production problem. Then hydrate production from Ignic Shikomi field in Japan. So this is the first test. Sorry, not Japan. This is in Alaska. First production done by carbon dioxide nitrogen injection method, swapping method, nitrogen swapping method. So they have planned the test in 3 steps. One step is injection of gaseous mixture of carbon dioxide, nitrogen and chemical stressor. Then they allow the well to flow back at the downhole pressure above stability for some time. Then they reduce the pressure below the stable region. That means depressurization. That means first injection, then flow back at the stable region, then we allow the extended flow back. That means at depressurization below your stable region. So mixed gas limit your when you are injecting this nitrogen carbon dioxide, this is acting as a flushing medium, also is displacing both free water and this also geochemical condition. The ratio of carbon dioxide and nitrogen was 77% and 22, at least 78 and 22 for 14 days. Total gas volume injected this much. Then they have certain period of 4 days because of operational issue, because of installation and changing the pump, jet pump. So then unassisted flow back for 1.5 days. Then initial jet pump assistant. That means initial period the flow back happens because of the reservoir pressure. Then after that they use the jet pump installed at the bottom hole on the other side of the gas leaf. So use this jet pump for 8 days. However, pressure is maintained above the stability zone, hydrate stable zone. Then again for 3 days, here pressure is at the stable zone. That means at 3 pressure zone. And this assisted phase flow, again jet pump assisted phase flow for 19 days. This during this phase they have decreased the bottom hole pressure below the 3-phase equilibrium pressure. That means you can say depressurization. So 70% injected nitrogen was recovered, while only 40% injected was recovered carbon dioxide. So from here we can see that we can successfully here in sequestering the carbon dioxide at almost 60% carbon dioxide trapped in the hydrate reservoir, So during flowback period, almost up to here we get 80% total volume of when unassisted flowback means after injection, when you open the well, so initially nitrogen and carbon dioxide come along with methane, because that whatever we have injected, that will return also, whatever free phase is there. So initial period, you will get injected nitrogen, carbon dioxide and methane in this stage. Then in this stage, they have there almost 80% of methane, and rest 20% is injected nitrogen and carbon dioxide. So when depressurization stage is up to here, this phase, they have almost recovered 97% of methane, and rest 5% is injected nitrogen and carbon dioxide. And also notice that the carbon dioxide never exceed 2%, which is good. That means successfully sequestered the carbon dioxide in the formation. Then this gas-added production from Nankai-Tro in Japan, the first offshore production done in 2013. So here hydrate saturation is up to 80%. Method of production they have obtained is depressurization. During 6 days of production, they have decreases the pressure in stepwise manner. First 13 to approximately 5 days, then maintain that 4 days, then again decreases to 4.5. That means whatever Malik field, they have realized that to reduce the sand problem to some extent, and also pressure should be decreased in stepwise manner. That's why they have implemented that technique here, that result here, and they are getting higher production compared to that Malik field. However, water production is also too high, and method of sand production was gravel packing. Then again, in that same Nankai field in 2017, they did 2 tests, one for 12 days, drawdown was around 7.5 and 41,000 methane gas produced here, and another well at the same around the same time in 2017 itself for 24 days produced this much of methane gas. However, here drawdown was less compared to here, because they could not increase the drawdown because of higher water production problem. Here in this case, since they have noticed that higher water production problem here in the first test done in 2013, now in this case they have isolated the lower hydrate saturation zone. See, in hydrate saturation, you can see here the hydrate saturation here is approximately 280, but this is not uniform. In that layer, some layer having hydrate saturation is less than 80, around 50, 30 also. So when you have lesser hydrate saturation zone, so that zone is contributing more towards the contributing more water production in this case, in this first case. That's why you are getting they got more water. So that's why in the next this second test done in 2017, they did isolate this lower saturation or hydrate saturation zone, so that they can reduce the amount of water produced, and they are successful in some way, but again sand production was a problem then in both wells. Then in South China Sea, first production is done in 2018. This is the longest duration of production, 60 days. They produces this much of gas. Depressurization, sand control, slow depressurization screen. Here instead of high depressurization, they are doing it by slow depressurization. As a result, they reported less sand. They did it in the 2020, recently concluded this one April, and they did it for 30 days of production by depressurization. The production, if you compare it, here it was in 3.9 around, here it is around 8.6, higher production, because they use horizontal well, and exploitation the horizontal well increases the surface area of well bore. That's why they increase the production. And for sand control also, they use composite 3-layer technology. Control technology, which consists coarse fine grain gravel packing, high precision pre-pack screen. But still, though they reported getting lesser, sand this time, but still scope, lots of scope is still there. So see here, one thing you can notice here is that the horizontal well can be used for increasing the production, because it increases the surface area. The basic funda is that only. And people are looking for hydraulic fracturing also, but recently from one study based on numerical simulation reported by Singapore, is that gaseous reservoir is too elastic for fracturing purposes. However, more results are still awaited. Similarly, for we can notice here that for any commercial production, we have to build a robust cell control program. Robust cell control technique. Then only we can move from this commercial production. So I'll skip this. Already I have discussed this, so I'll skip this slide. So next I'll move to this our India's gas added program. India started this national gas added program 1 in 2016 to find out this gas added potential in Kerala Konkan offshore basin, Krishna Godavari on Mahanadi offshore, and in Andaman basin. And this site selected based on the preliminary seismic studies done by various organizations including ONGC, DGH, and others. Based on the BS bottom simulation reflector, they have this shortlisted this three: Kerala Konkan, Krishna Godavari, and Andaman basin. And out of this, they have selected one site here in Krishna Godavari, Kerala Konkan basin, 2 side in Godavari basin, and 6 side in Kerala Konkan, and 1 side in Andaman. And based on these, their observation, based on their study, they have noticed that they have found gas added in Kerala Konkan basin, Mahanadi, Krishna Godavari, and Andaman, but could not find any hydrate formation in the Kerala Konkan basin, though BSR bottom simulation reflector shows the hydrate formation. And this is because they have found that this BSR is because of lithologic changes only. So here in this Mahanadi, Godavari basin and Andaman Sea, one of the thickest gas hydrate accumulate discovered in Krishna Godavari basin, and one of the deepest hydrate 600 meter below the sea floor was discovered in Andaman. Most of the hydrate discovered is fracture reservoir, as I have already told. Then most of the discovery was by microbial process, that means biogenic origin, that means obviously methane gas only, structure 1 hydrate is there. Then in 2015, India completed second gas added program, National Gas Added Program 2. The aim was sand dominated reservoir. That means sand dominated means pore filling reservoir having this Orser grain structure. So reasonably compacted sediment, occurrence of free gas below 1. That means looking for structure this class 1 hydrate. Class 1 hydrate is free gas below this. So they have a logging and various coring and pressure logging, wireline coring, pressure cooling done, and based on this, they have confirmed the Krishna Godavari this Krishna Godavari, this region B and C of this region, they have discovered the same dominated reservoir. 2 areas in Krishna Godavari region B and C. That means here Krishna Godavari B and C, this zone around this Visakhapatnam area, and this here, this C zone, they have determined find sand rich system. That means coarser grain sand rich systems, ideal candidate for future gas and production, and find hydrate saturation ranges 50% to 100%. Obviously, we don't want 100%, but we require more than 50% reservoir this hydrate saturation. So and in third step, they are India's planning a third National Gas Added Program 3, where they are planning to drill at least one pilot well in one of these areas, this area B or C. Last, the production of gas hydrate is associated with environmental and geomechanical issue also. Environmental impact is because of the production of methane gas released into the atmosphere. That will be a very big problem, because methane is 21 times more potent greenhouse gas than compared to carbon dioxide. See, combustion of methane is safe, but release of raw methane into the atmosphere, that is very hazardous, because it is more greenhouse gas. So if because of the production that will be released, that will be a huge problem. However, there is no scientific basis, or there is no observation around the world also that this can be released. There is a release of methane continuously into this environment because of this production also. Also, this mechanical hazard, because of if we produce from some load bearing sediment, there may be a disaster of formation collapse may occur. So or wellbore stability also you have to look. So we have to this environmental and geomechanical issues are we have to look before going for full scale for commercial production here. So this is the summary. Natural gas is considered widely as an alternative form of energy because of tremendous reservoir. Several countries already started, in their pilot scale study. However, low production, hydrate regeneration, sand problem are still to be solved for before going for commercialization. So these are few references you can refer for more information. So thank you. So if you have any question, you can ask me now.
Thank you, Himanshu. It was a nice presentation, lot of information, lot of data.
Thank you, sir. So if you have
So any query from the audience?
Hello, am I audible?
yes,
Hello.
yes, yes, you are
Yeah,
audible.
doc Dr. Himanshu sir, I would just like to ask you one point that I had in my mind. Is depreciation working more better than the thermal methods in methane extraction? I mean,
Yes, depreciation works
hydrate
better than
extraction?
because as I have shown you here, you can also see there in Malik field, after the production they have calculated the efficiency and efficiency means the heating value of produced gas by how much energy you have spent by running the pump. So it is around 10% initial time. But initial, as you know, initial test in the 2000 interrupted because of high sand production, and the later one in 2008, they got around 30% greater than the consumed power. But in when you
Sir,
compare the uh,
I
yes,
had
tell
in my
me.
mind can't this depreciation and heating go together in the reservoir? It is a
Yes, yes,
simultaneous process.
yes, yes. That means more instead of going alone, that means depressurization or this thermal steading combination is a preferred mode because that can be by combination method you can remove few of these difficulties obviously, but there is no data to, this practical data to support this hypothesis. Only you have this numerical analysis is there, numerical simulation data is there, but there is no this type of practical data where they have simultaneously produced from both depressors and thermal methods. However, numerical data shows that you will get better efficiency compared to this either depressurization or this thermal.
Thank you. Thank you. Thanks a lot.
Anyone else?
Dr. Dr. Himanshu, I have a small question for you. What are the main challenges that are faced during the production of gas hydrates?
The main challenges faced during this pilot study was that one is this high water production rate. High water production means because when we go for commercial production, we cannot go for high water production because we have to dispose the water. And if we are thinking about injecting water, we have to remove the salt because we cannot inject high saline water into the reservoir. First thing. Second problem is sand problem. Sand problem we have to solve because of the since either going by depressurization or any method, even in the carbon dioxide sweeping method also, when we have this mechanical equipment is there, we cannot afford high sand control because when this mechanical equipment is there, when sand is high, that will erode it. So sand control we have to, bring it to our level so that it can we can go for the commercial production. Then one another challenges they face is effective permeability. Initial effective permeability means when we go for hydrate production, obviously looking for higher hydrate saturation, but higher hydrate saturation decreases the initial effective permeability for gas or water. When initial effective permeability is less, pressure response travel in the reservoir is less. So that's why that's one problem they are getting. And also for getting higher effective permeability, we cannot choose the lesser hydrate saturation reservoir also, because lesser hydrate saturation means again we get less amount of gas. So that is one problem initial. So these are few problems, sir. Main problem we have to solve before going for commercial order.
Okay, thank you. Any more queries?
Hello.
Yes.
Yeah, sir, I had one more question in my mind. Like, how different is the depreciation process from CBM? Like, CBM also we produce via depressurization. So, how different is the process?
Actually, in gas hydrate, by depressurization, we are changing the pressure and temperature condition of the reservoir. As a result, the gas molecule comes out from the hydrate structure, because in hydrate structure, gas molecule is inside the cavities formed by the water molecule. So when we depressurize it, when it brings the condition outside the stable region, the hydrate is no longer stable. So gas is coming out of the this water structure. But in case of CBM, when we depressurize it, the gas is deabsorbed from the matrix surface. That is in case of CBM, that is surface deabsorption. But here in case of the gas hydrate, the depressurization is meant to destabilize the structure. Destabilize the structure means destabilize the hydrate crystal, so that the gas can come out of the water. But in case of CBM, the depressurization is meant to deabsorb the gas molecule absorbed on the surface. That is a surface phenomena. Here it is to destabilize the pressure and thermodynamic condition.
Thank you, sir. Thank you.
Anyone else?
Any more queries? So if there is none, I'll give the end remarks. So on behalf of everyone present in the program, I want to thank Dr. Himanshu Kakoti for his informative and interesting presentation on the very important topic of exploration of unconventional hydrocarbon. We appreciate the time you used to share with us your knowledge and expertise. Your lecture touched so many critical areas pertaining to gas hydrate, like their exploration, types of hydrates, different methods of gas formation, production, along with the case studies showing the gas hydrate production in different areas of the world. So thank you, Himanshu. Thank you so much once again from all of us. Thank you very much for speaking to us today. Thank you.
Thank you. Thank you very much.
So with this, we come to the end of day 4. So on behalf of the Department of Petroleum Technology, I thank all the participants for joining and attending the sessions of day 4. So my sincere thanks to the resource persons also for sharing their knowledge and expertise. So we meet again tomorrow at 10:30 for the last day of the FDP. Thank you all of you.